Please take your seats. Our session is about to begin.
As an OCP member, you have the opportunity to join hundreds of active member companies and thousands of engineers working together to reimagine our world's hardware infrastructure and increase the pace of innovation through a framework of open collaboration. And when it comes to getting the most from your OCP membership, it's critical to listen, understand the community, share your expertise, and build trust. Why? Because OCP isn't merely a place to buy and sell. It's a true community. And like any community, you get out of it what you put into it. By actively participating, you gain better insight into the community, its processes, the challenges that organizations face, the solutions that are currently available, and how the community is addressing tomorrow's growing technology demands, placing you and your organization in a better position to achieve your goals, whether it be marketing your equipment in the OCP marketplace, adopting OCP gear, or building out your own facility. After all, one of the most important benefits of participating in the OCP community is the ability to drive innovation and enhance the hardware and software you rely on every day, not just for your organization, but for the industry and data center ecosystem as a whole. So become an OCP member, participate in projects, add to the conversation, share your expertise, attend events, or run for an OCP leadership position. There are countless ways you can take part in our community and in reimagining our world's hardware infrastructure. Discover them all at www.opencompute.org.
Please welcome Chief Executive Officer of the Open Compute Project, George Chaparian.
And welcome. We are very excited, my team and I, to be here in this beautiful city and venue with you today. And equally and more excited to bring our summit to Europe. Let me start by introduction of two members that joined our extended OCP team. We're fortunate enough to have David Rumku from Meta be part of our OCP board. He's here today, and he is supporting us. I'm sure you're going to run into him. And also, after so many years of volunteering, Rob decided to come to us permanently, and we hired him. He is the Community Technical Program Manager to help you bring in your contributions easily into OCP. We were here in 2019 in Amsterdam. It was a great success there. Unfortunately, then, the COVID hit, and for the past 3 years, we couldn't come. But like I said, we're here today, and we are very happy to bring it back. And I'm going to give a shout out to some of our members and partners that we work with, because we never left Europe. We always work with you guys, with our community. Here you can see some of our members and partners working with us, embracing the OCP Ready program, a co-located program, and as you can see, we have so many of them in this space. Thank you for that. And likewise, in the same vein, we work with the greater EMEA community, and here we also have the OCP Experience Centers where you can go in person. They give us their footprint, they help us, and you can go there and see and witness and enjoy how the technology is coming together in their data centers. You can see where they are in the greater EMEA. Now, so to those of you that don't know us or new to our summit, I would like to take a few moments to explain who we are. At the core, we take hyperscale open innovations. We curate them as a bridge. We seed the market and shape the market and make sure that those innovations are transformative, standard-based, and deployed in the industry for all of us to enjoy as an open source, open community. So as you can see, at the core, we have 5 tenets. And it has to be open, it has to be efficient, scale, and also impactful. And last year at the Global Summit, we added sustainability because this is really key for our global and collective way, inclusive way to address all these issues that we face, as all of you know. And I'll urge you to go to our website to learn more about those tenets. And because all the projects and all our ideas go to this rigor and make sure that they are, addressing the mission and the vision which we are completely, passionate about, and also consistent throughout the years since 2011 when OCP was formed. With that, we have a great momentum going forward. Today, I can tell you that I'm very happy to announce that we have more than 335 or 340 members, active members of OCP around the world, and 6,000 global active participants. We have followers in social media, more than 40,000. And when we do annual events like this here and globally, we assemble 6,000 people per annum, and also virtually around 10,000 people attend our summits or follow up our presentations thereafter. And of course, most importantly, also we partner with our sister divisions, sister organizations and consortiums out there. As you can see, these are very important for us as alliances to make sure that we're not duplicating the efforts and we're really helping each other to converge on the right pieces of interfaces or pieces of modularity of our products and innovations to come together to serve the community. And we do it with you. We do it with the community, by the community, and for the community. Another way of approaching this is we want to let you know that we have a marketplace where you can go there and look at our vetted solutions, whether it's hardware and software coming together, and you can actually go there and pick those up with the right interfaces and modules and start your own supply chain, start your own business development. We have 200 of them today in the marketplace. And we have about more than 300 contributions, whether they're specifications, whether they are designs, white papers, ideas, and you can see how rich this is getting through the whole industry and how we're shaping, innovating the industry. One thing that I also like to comment that AMDIA is a research and analyst firm, independently done the research, and they do it every year for us. And I'm happy to report that their analysis is that by year 2026, we're going to have about 33 billion euro market from our OCP recognized products and solutions out there. So this is huge. As with all the challenges I'm sure your companies are facing, we live it every day. All these challenges come to us like efficiency, sustainability, the AI, the whole notion of how we're going to be able to really take care of these workloads, security, privacy, and so forth. So we live it every day, and with you all. And we also are exposed what's coming up and what's going on because because we're fortunate enough to be in the center of it. The reason I say this, I want you to come and join us and help us because we need help. We have about 40 work streams out there. Come join, be part of it, bring your ideas, let's get together, and collectively address these issues that's coming out. These are challenges that we're facing today. And these are the challenges that I'm sure you know we're going to face together going forward as the future challenges. Again, the evolution of AI, how it's going to be played out in so many ways, from technology point of view, from all the way to the regulations and so forth. And the quantum computing, high-speed computing, it's going to become very important and central going forward. And I don't want to read through all these about regulatory challenges, utilization, and the whole aspects of cooling, heat reuse, and you name it, we have it. But the shout out here is the call for action is here, like come join us and be part of this journey to shape and seed and shape the innovative culture and the industry going forward. So thank you and appreciate it. I'm glad you're here. My team put together a very solid 2 days for you here with the esteemed keynote speakers we have with a lot of information. And now I would like to bring on the stage our CTO, Bijan Naurouzi, and our chair of Future Technology Symposium, Leslie Demid. Okay, thank you very much. Enjoy the summit. I'll be back.
Good morning and welcome to the OCP Regional Summit. We are so excited to have you here.
So I've got a couple of quick announcements, then I'll tell you what they're why they're important. The first one is I really want to recognize 2 outstanding projects and 2 outstanding results. So both of these pertain, there's one per project, and let's go through it. The first one is from our Open Domain Specific Architecture group, and they have 2 actual specifications that they're releasing, and this is huge. It helps to create an open chiplet economy. The first one is bunch of wires 2.0. So there was a 1.0, it was on the market, it was the first chiplet specification, and it really kind of made waves in the industry. This is 2.0. It's twice as fast. It has advanced power management that cuts power about 90%, and it allows enormous flexibility in deployment. The second part of this is there's a new link layer specification that allows a lot of robustness and flexibility. There's error correction, there's all kinds of things in here that allow IC designers to be very flexible when they design chiplets. So it's a huge milestone, and we're going to be making some press releases, and there's a lot more that you could learn. There's an engineering track tomorrow. It'll be in, I think, 2A South Hall, so please join. You'll have a lot to learn. There's a whole track planned. Next announcement is we're announcing, this is very exciting, Enterprise Edge Gateway. And so where this fits in our portfolio is we already have an exciting product. It's an open edge server that's very popular in mobile edge computing and also Open RAN, things like that. There's also something that we announced at Global Summit, and that was the DC MHS, which is the Data Center Modular Hardware System. It's a very advanced, flexible design. Both of these are very edge optimized, and where this fits, the Enterprise Edge Gateway, is that it allows the creation of a standard platform for compute, connectivity, like IoT gateway, all kinds of things that you can do. There's a whole other keynote coming up, so I don't want to steal their thunder, but I just wanted to say that this is going to be a big announcement that we're going to make in the press. You'll see some more of this later. Thank you.
OCP has taken steps to build and shape the future of our industry. So the first one is the OCP Future Technologies Initiative, which is a project-based collaboration between the research, industry, startups, communities, with a purpose to build future opportunities to identify deep technical challenges and accelerate productization. At this moment, we have 3 work streams: AI hardware software co-design, cloud service model, and computational storage. So I'd like to invite you to join the FTI workstream, collaborate on the long-term challenges and opportunities together with us. Second, the OCP Future Technologies Symposium is a biannual event that spotlights promising future technologies in our industry and showcases the results and strategic outcomes of the FTI. Today, I'm so excited to have you and invite you to the keynote presentation of the symposium with AI, HPC, quantum, neuromorphic computing, heat reuse, and data sustainability. The symposium will take place this afternoon from 1 until 5. We also have a technological demonstration where you will see the prototypes, model, and recent developments from the European startups. So please join us at the symposium this afternoon. And today, we have an exciting announcement. Historically, OCP brings hyperscale innovations to open community. At the same time, we realize that startups are rapidly developing innovations and seek ways to bring these technologies to the market. We realize that by bringing these two worlds together, we can achieve a high level of impact for our industry. So, we are introducing the OCP Startup Program to unlock high level of collaboration between the startups and the whole OCP community. The three-tiered program is tailored to meet the needs of startups at each stage of their growth. As a result, we aim to achieve an integrated ecosystem and community that is truly shaping the future of our industry for years to come. To learn more about our program, please visit the website using the QR code. Thank you so much, and we'll see you this afternoon.
Thanks, everyone.
Please welcome Meta's Open Source Ecosystem Lead and OCP's Incubation Committee Co-Chair, Dharmesh Jani.
Imagine making an inquiry that echoes through the generations, changing the course of humanity. 127 years ago to this month, on the campuses of Stockholm University, this brilliant scientist asked one simple question. Does the surface temperature of ground in any way depend on the heat-absorbing gases in the atmosphere? His name was Svante Arrhenius. And with this one profound question, he set the humanity on a path which in some small way has brought all of us here together. Good morning and welcome everyone to this OCP Regional Summit. We are back after 3 years and I'm delighted to be here. And what a week we have chosen to get together. This is Earth Week. So let's pledge to work together for a greener tomorrow. I'm also equally delighted to share the work of my colleagues at Meta. So without further ado, let's get started. Svante Arrhenius was also the first individual to propose the link between human activities and level of carbon dioxide in the atmosphere. That was April of 1896. Generations came and went by without realizing that there were changes happening in the air they were breathing. It was not until late 1950s when one Charles Keeling started measuring carbon dioxide levels on top of Mauna Loa in Hawaii. His meticulous measurements lasted 30 years. Keeling curve, as they are known today, show a clear and continuous rise in carbon dioxide levels. These measurements continue to be taken well into 21st century, and the trend continues. 21st century was also the time when the world entered into the internet age. Many new companies were formed. Facebook was launched in 2004 with a mission to empower people to build communities and bring world closer together. Today, Meta products power 3 billion people on a daily basis to exercise this on globally. In the following year, Kyoto Protocol entered into full force, and then the world continued to work together, and in a historic moment, 196 countries came together in 2015 to sign the Paris Climate Accord. This decade was also a transformational decade for Meta. We started our sustainability initiatives internally, launched teams, and set milestones. All of this culminated into 2020 being a landmark year in the history of Meta. We achieved net zero operationally for the first time in our history. This was in great part by use of 100% renewable energy. This powers all of our data centers, and with over 8,000 megawatts of renewable energy portfolio, Meta has one of the biggest for any company. 2020 was also the time when we restored 5.8 million cubic meters of water. That is a lot of water. I was trying to get my head around it. And recently I learned some interesting statistics that Czech Republic is the #1 nation when it comes to per capita beer consumption. This amount of water can provide Czech Republic uninterrupted 4 years of beer. Now that is something we can say cheers to, yeah? 2020 was also the time when Meta announced its boldest goal of achieving net zero across all of its activities, scope 1, 2, and 3. And that's the destination we want to be mere 7 years from now. So that begs the question, where are we today? Let's look at our 2021 numbers. We are going to publish 2022 numbers in the middle of this year. In 2021, Meta reported 5.7 million metric carbon dioxide emission in the atmosphere. This includes all of its activities. But when you go and take a closer look, you find that scope 3 constitutes 99% of the emissions which Meta has reported. These are the areas where Meta is working, and activities across all of these domains contribute to these emissions. And we expect these emissions to continue to rise going into 2030, perhaps 2 to 4 times what we have reported in 21. That is the challenge we have to address today. So what is our game plan to bring this number down to 0? Meta is a reduction-first company. What it means is decarbonization is the first lever we are going to use to bring the number down. All of you saw scope 3 contributing the biggest chunk. Engaging suppliers is a very important component of bringing this number down. Whatever is left over, we are going to use carbon removal projects, and we hope to achieve net zero by 2030. All of these 3 ideas are being worked on right now. And I want to go deeper with you to see how and what we are doing in each of them, starting with decarbonization. Decarbonization has 3 pathways which we are working on. First, you start with consuming less. Next, you do a better design with circularity embedded in it. Third, you work on innovative materials and fuel technologies, and all these 3 combine to bring the number down. Let me give you some examples to relate to all of these things we are working on. All of these buildings we see, cement constitutes the biggest carbon footprint. Meta is working with new materials like clay, ash, powdered glass as a component of cement up to 20 to 30%. And what we are discovering is we can bring carbon footprint down by as much as 40%. That's a big reduction. Next, we are transforming all of our data centers, making them more circular, bringing more compute, and making them denser. Third, we are using generative AI technologies to look at new innovative materials to explore direct air capture of carbon. We are also looking at alternate fuel technologies to replace our diesel generators, which are powering backup power right now in our data centers. That is lever 1. let's look at how and what we are doing with suppliers. We started a supplier engagement program. The first goal of this program was to work with our suppliers to get them to benchmark. What you cannot measure, you cannot control. So you have to start with benchmarking first. Once you do benchmark, then you figure out where you want to go and set targets. And then we work very closely with our suppliers to set the roadmap which intercepts with our goals. Our supplier engagement program started a couple of years ago. And in 2021, we had around 40 suppliers as part of that program. In 2022, that number went up to 116 suppliers. In 2024, we are expecting suppliers representing 2/3 of our spend as part of this program, or 80% of our carbon emission. The last lever I want to talk about is obviously carbon removal, and the philosophy here is very simple. We want to use nature-based, and we want to use emerging technologies. Whatever project we choose, it must satisfy each of the 6 criteria. First, it must be designed for permanent impact. No release of carbon allowed even after extended period in the atmosphere. Next, we want to work on these projects with communities, making sure that their ecosystem, biodiversity, and economics is maintained. Projects must demonstrate additionality, which must be measurable, quantifiable, and auditable by the third party. This is where we are working in terms of our strategy. However, we do have challenges ahead where we need help. There are several challenges we have to bridge. I shared all of these at Global Summit last year in October at San Jose, and because these are important, it's worth repeating them again here. I call them big, hairy, audacious goals, starting with embodied carbon in silicon. Silicon powers everything in our data center, from compute to networking to memory to even AI and machine learning. Understanding its footprint is a table stake. I talked about circularity in decarbonization process. This is important because when you extend the life cycle of the components and devices, you effectively net out and reduce your carbon footprint. Now, this is not only a technical challenge, it's also a business challenge, which requires us and all of you to work together to figure out how we create new business models. And last but not least, power usage efficiency is something we are all familiar with for measuring data centers. However, as I said, we have to measure what matters. Carbon is an important point we are optimizing, and that's where we have to come up with new measures. And all of these 3 things we have to do with collaboration in mind. And that's why I'm sharing all of this with you, because these are the challenges which we need to work together. So what exactly has Meta done on collaboration front? Actually, I'm very pleased to mention that Meta was the first company to bring sustainability as a strategic initiative within OCP in 2019. We proposed this to incubation committee. We worked with the broader community for 2 years to define, refine, create mission, create understanding, and in 2022, Meta was instrumental working with others to bring this as a top-level project. You can learn more about it. You can go to the OCP website. That's one area we are working on. I'm also very pleased to announce for the first time here, Meta has joined forces with IMEC out of Belgium. IMEC, as you know, Inter-University Microelectronics Center, does a lot of cutting-edge research on semiconductor processes, working with broader semiconductor industry. I mentioned embodied carbon in silicon is important. Actually, understanding carbon in the entire manufacturing process of semiconductor is important, and that's the goal we have here. We have joined the Sustainability STSS program. So that begs the question all of you must be wondering, this is great. What can I, sitting here in audience, do? Actually, we all can do a lot via Open Compute Project. So let me share with you one idea which you can all take with you and start participating as soon as you start thinking about it. We are launching a new work stream within sustainability project, and this work stream is going to address figuring out new ways to measure sustainability, understanding power telemetry into devices like server, networking switches, storage servers, and even racks, and then looking at carbon modeling, because that is important and that requires all of us to work together. It's not a problem which can be solved by one company alone. And I keep using word we. Who are the we I'm talking about? These are set of individuals from these organizations who have come together. We are going to share more details about this particular work stream. We have an upcoming sustainability workshop in Portland, Oregon in July of this year. It's going to be both in person and virtual. I encourage you to track details about that on the OCP website, and please join, either in person or virtually. I extend this invitation to all of you because we must do that for sake of pale blue dot. This is an image inspired by Carl Sagan. As Voyager was leaving our solar system outside the orbit of Neptune, late astronomer Carl Sagan requested its camera to be turned one last time to take a picture of our Earth. This is Earth from 6.5 billion kilometers away. It's a mote of dust hanging in sunbeam. This is the only place where we know life flourishes. From the simplest of the cell to the biggest of the blue whales. From the slowest of the snails to the fastest of the peregrine falcons and cheetahs. From the simplest clump of neuron in a jellyfish to the complex brains which we carry in our skull. Each and every living organism has right to this Earth. In this cosmic darkness, this is the only place where we know life belongs. So we must protect this fragile pale blue dot, for this is the destiny we all share. Thank you very much.
Please welcome Open UK's CEO, Amanda Brock.
Good morning, Prague. It's a great pleasure to be back here in Prague for the first time since lockdown. And in fact, to be on a stage in Prague for the first time in almost 20 years. I doubt anybody in this room knows that I used to work here around 20 years ago, pre-accession. And I worked for an electrical retailer, a company called Dixons in the UK. We set up something called Electro World here in Prague, in Zličin. And we sold computers for under 300 euros for the first time in this country. And I'll never forget, on our opening day, the highways of Prague came to a standstill for the first time since the Velvet Revolution. We made the 6 o'clock news here in the city. I doubt very much that the content of my talk today is going to have quite the same impact on the city, but I do hope that you'll take away a few things about open source and whether or not it's going to fail. So for the last 3 years, I've been CEO at Open UK, but my background is as a lawyer. And 15 years ago, almost exactly, I joined an open source software company in the UK, Canonical. Canonical, you may all know, I was employee 185. It's much, much bigger today, and it's the commercial sponsor of the Ubuntu operating system. Since then, I've been very engaged in open source software, also open hardware and open data, but primarily software. And I have had a number of different roles as a member of the community, one of them being with the United Nations, where I chaired the Technology Innovation Labs. I have a government appointment in the UK with the Cabinet Office, with the Open Standards Board. And last year, I was elected to the Open Source Initiative Board. And the OSI is the custodian of the licensing, the custodian of the open source definition. For my sins, I edited a book. It was a difficult 5-year process, to be quite honest. It's 640 pages long. I suspect I'm going to be the only person in the history of open source who reads that book cover to cover 5 times anyway. But you'll find, if you're particularly interested in the hardware space, that the second last chapter by Andrew Katz, who is the world leading authority in open hardware licensing, might be right up your street. We launched the book in All Things Open, an open source conference in Raleigh, North Carolina, in October last year. And we launched it with 6 different female authors on a panel. And that panel, unexpectedly, went viral on the Chinese internet. Who knew? So the book has now been translated into Mandarin, and it will be published there later this year. So I do academic writing, I do tech press writing, and I do a lot of this. I travel the world speaking at conferences like this. And often what I'm doing is explaining open source software. Back when I joined Canonical 15 years ago, it was really, really difficult to get open software, open source software, open hardware was sort of a vision, adopted. And what we found was that there were barriers, risk-based barriers, compliance-based barriers, and they came from procurement, they came from legal, and they came from finance, because people needed approval to bring open source into their industry, into their businesses. And I think it's really important to understand what open source software is. And open source software is software where the source code is made available, and that source code is distributed on an OSI-approved license. To be in an OSI-approved license, it needs to comply with the open source definition. And we're lucky to have a definition, although even that compliance can be debated in our space. For me, principles 5 and 6 are the critical ones. No discrimination against persons or group, so no discrimination against people, available for everyone to use for any purpose. And any purpose is no discrimination against field of endeavor, 6. On the open hardware side, we don't have quite the same definition, but I recommend the book chapter to help you with that. We also need to be thinking about open silicon and how that works. Now, we see today a very different marketplace. Between 48 and 98% of any software that you see today is going to be open source. That percentage depends on the surveys you look at, it depends on the stack you're talking about. And that's because of a shift. And there's been a massive shift away from open source being blocked by those procurement, those legal, and those finance people because of digital transformation and digitalization. And what we see is the role of the engineer elevated in organizations. As a company becomes digital, it needs its engineering function to support it, and the engineers start to become decision makers. For the software side, we see Git. We see Git as a tool and the repositories that allow collaborative working, distributed working like GitHub, GitLab. We see them making it accessible and easy for those engineers to bring the software into their organizations. And we see cloud. Cloud is built on open source. There's no denying it, particularly the public cloud. And what we see is companies shifting from that contract base to thinking about their policies and their processes around open. And we see Microsoft as a great example. So Microsoft was one of the biggest opponents when I joined Canonical to open source software. Today, it's the single biggest contributor in the world to open source software. So what makes that shift? Steve Wally, my friend, Steve Wally was speaking in Edinburgh in 2018, keynoting the Open Source Summit there. And he explains that Microsoft's shift isn't altruistic. He explains it's for 3 reasons. Firstly, anybody who's learned to code in the last 20 years is going to use open source. They just are. It's the way that they work. And if you want to hire them, which most people do today, you have to allow them to develop in an open way, to recycle, to reuse, to collaborate. The second thing Steve says is that we now today see technology, particular innovations, things like containerizations that customers want that are only available open source. I just left Amsterdam last night where there are 10,000 open source software developers at KubeCon. This is permeating our society. It's the backbone of it. If you want to run a cloud business, you don't just use the open source software, you have to engage with those communities. You have to be part of it to have influence. And then the third thing that Microsoft say is that the customers today really want that software. So you've got the engineers, they want to use it. You've got the customers who are asking you for it, and to run a cloud business, you need it. And what we're seeing is sector by sector, they're following that journey that Microsoft has been on. They're following that shift. At MWC this year, we saw the GSMA launch Gateway, their open API project, and many companies like Nokia and Rakuten also made open source announcements. In the public sector, the UK's had a leading position, and for the last 11 years, we've had an open first strategy. That became really apparent, not just in the UK, but globally through lockdown, when we saw the test and trace apps across the world open sourced. But it's not just that front end, it's not just that user-facing piece. We also see the backbone, the infrastructure, our national critical infrastructure being built in open source. So obviously we've won, but now what? Well, when open source comes into a marketplace, it disrupts, and that disruption often affects revenue generation. So you can understand that there's a lot of pushback. There's a lot of pushback from the disrupted. Nobody likes to lose revenue. And as a consequence of that, we see a lot of FUD, fear, uncertainty, and doubt. And it's still a problem for us today across many different areas. We may have won a battle, but we've certainly not won the war. And what we see is things like concerns about that infrastructure, that critical infrastructure being built on open source software. We see security concerns. I was just backstage reading an article this morning about open hardware and security. First one I've seen, very good. We see standards. I was pleased to hear George calling for more open standards on which we base our future. And we see geopolitical shift. We see governments who are not so keen on collaboration across the globe, which is at the heart of everything we do in the open source spaces. And that geopolitical shift can have massive, massive impact. We see things like the war in Ukraine even with protests were trying to restrict people's usage, trying to restrict the purpose of the usage against those fundamental principles I mentioned at the start, principles 5 and 6 of the open source definition. So, we've won, but can we make our future sustainable? In the UK, the way we've been doing that is through Open UK, the organisation I run. And we do it through the 3 opens. John Laban, I believe, isn't here today, but I know many of you know him. And John christened these as the 3 opens in our first board meeting. John's one of our directors. Open source software, open hardware, and open data. And we believe that the 3 opens are necessary for the future. We bring together a leadership community to build a cohesive voice, and we do that by celebrating them through awards, through honours lists, through bringing them together in events. We use their power, we use their collective voice in our geography to influence law and policy, responding to legislation in the UK and abroad, and building reports. These are our first reports from 2021, where we cut the data for the UK for the first time. We looked at case studies across the UK, and we started to tell stories that the policymakers, the governments, and the business people could understand. In 2022, we used some of the data to demonstrate some key facts. If you look at that top left one, you'll see the amount we estimate was invested in the UK in open source software. So for the UK, that's 5 times the amount that was put into the Digital Recovery Fund and the Levelling Up Fund for tech. 5 times, quite incredible. We've also been very involved in the sustainability agenda. And we had one of the biggest events at COP26 2 years ago. This year we're hosting an event in Edinburgh on the 14th of September, sponsored by Intel, where we'll look more at the work we did before for COP26 and the work that we're doing now for COP28. At COP26, we launched something called Patchwork Kilt, the data center of the future, using open technologies, bringing together a blueprint for open source software, hardware, data. I loved what I just heard before I came on stage, and we already have a lot of OCP included in this project, and I hope to see more of you engaging with us. Initially, this community was being built by the Eclipse Foundation, but we've taken that back into Open UK, and we're building it out for COP28. We also have an EV charging blueprint setting out the various aspects of open technology and EV charging. Security is high up the agenda. I've mentioned it already. It's a great challenge in open source. It's a challenge also in open hardware. And last year, we launched our first summer of open source software security. We will do a second this year, which we should broaden to cover hardware too, I realize. And that was very recognized as one of the 8 key initiatives. So we bring our community together. We use their voice to have influence, and we build skills, we build learning. We do that for children, we do it for business people. We're working with Strathclyde University's Entrepreneurship School, and later this year we'll launch a MOOC, a massive open online course. And all of this drives to our purpose to meet this challenge around open technology. For us in the UK, we want to develop UK leadership. I'm sure you all want to do that in your own countries. But we also want to do it on a collaborative global basis. We're an organisation that's tiny. We have 2 full-time staff, but we have around 130 people, many of whom I know you'll recognise, working as our board, our leadership team, our ambassadors, helping us with different meaty problems that we tackle, and helping advise us. And right now, we've just launched 2 new advisory boards, one on AI and one on quantum, if anybody's interested in helping us. And in doing all of this, we've created a very, very different organisation. At the heart of it, we think there is a sense of belonging. That culminated in our conference, our first annual conference in London in February. We had just under 800 attendees, and incredibly, 88.3% of those who signed up attended. Now that could have been because OCP ran the hardware track for us, I'm not sure. What we also had was almost half our speakers who weren't men. When we look at our delegates, 1/3 of our delegates were women, and 49.7% weren't white. Something that I'm sure you all want to encourage, but something we rarely see in tech. So how are we going to build this future? How are we going to meet the challenge of whether open source will fail? Well, I'd ask that we collaborate more. I've mentioned that OCP hosted our hardware track. I hope they'll do it again next year, and that we can do more collaboration. Collaboration in events, collaboration in projects, collaboration in teaching. And I hope you'll work with us to understand curation, the good technical hygiene, and the good governance of open source. Collectively, we see responses have more impact when we deal with government. This morning, 13 open source companies submitted something to the European Commission on the Cyber Resilience Act and the problems that it will have in open source software. George talked to you about open standards. Collaboratively, we should build more of those. And we must demonstrate our value. We must demonstrate our value to other enterprises and to governments. Back in 2021, we released these details of open source software in the UK. You can see at 43.15 billion going up to 46.5 billion with a bit of tinkering, direct contribution to GDP. That will only go up over time. We need governments to understand that as they use more and more open source software, open hardware, and open data, that they need to contribute. And that contribution should take the form of recognizing the opens, recognizing open source as a digital public good. And today we hope to share with you, it could be tomorrow, but I'm really hoping it's today, our latest phase 1 report for the state of open, the UK in 2023. And one of the key things that we're going to draw out in that report is the position of the UK in Europe. In terms of open source software, we're number 1 in Europe. We're number 1 by the number of contributions made, the number of developers, and we're number 5 in the world. That probably surprises most of you because it's not something our government, it's not something our policymakers or our businesses talk about enough. And what we've demonstrated in this report, working with GitHub, is that in the UK we have over 3 million GitHub account holders. That's 4.5% of the UK population has a GitHub account. More than any country in the world, and I think you'll agree, quite incredible. So my messaging to you today is, will open source fail? There are many, many challenges. There's a great deal of FUD, and if we want it to be there and to shine bright for our future, that will only happen through collaboration and working together. Thank you.
Please welcome Broadcom's Senior Vice President and General Manager, Core Switching Group, Ram Valega.
Hi, good morning. Hopefully you all are enjoying Happy Prague as much as I am. It's been a beautiful city. It's actually been great to see a lot of friendly faces around in Prague. Today, you'll probably hear a lot about sustainability. You know, I was looking at the agenda. There's a lot about quantum computing, In between all of this, what I want to leave you with as you leave today is the key to enabling compute and open compute as you know it is all about open networking. And nothing comes closer to open networking as networking that's based on Ethernet. And I want to share with you some of the advancements in Ethernet, especially when you think about this whole world where you're hearing a lot about generative AI and a lot of ML AI, how Ethernet and Ethernet-based networking is enabling the next generation of compute. One of the things that you've probably heard about for the last many years is this notion of Moore's law coming to an end. It's something that we've enjoyed for the last 2 decades, right? That every 18 months, the transistor density was going to keep doubling. And the doubling of this transistor density allowed compute and the acceleration of compute like you've not seen before. Now, a few things that are starting to happen in Moore's law. First, as you went from the 16 nanometer process nodes to the 7 nanometer process nodes, you got about a 35% increase in performance. Now, when you look at going from 7 to 5, you're getting less than a 10% improvement in performance. Not only that, another thing that's going on is the cost per transistor is actually going up. When you go to TSMC and ask them how much more expensive a transistor is, when you go to a 5 nanometer versus a 7, it's actually 20 to 30% more expensive. And another secret that nobody generally talks about is the maximum size of the chip that could ever be built continues to be the same, which is about 800 millimeters square, right? So now think about it. The transistors are not getting any more efficient. The maximum size of the chip that you can build is pretty much remains the same. So how do you actually continue to scale compute, right? And for the last about 20 years, some of this problem has been solved. Historically, you've probably heard about mainframe computing, where you had these very largely integrated, boxes with large CPU, monolithic applications running on a mainframe computer. But starting in the 2000s, you've seen the likes of Google, the Google Clouds, the Metas, and the Amazons, and everybody else. What they said is, look, it doesn't make sense to build one large computer. It's better to actually build a computer by taking a bunch of smaller pieces and then distributing them, right? And so the whole idea of a cloud computing started to evolve. And when you think about a cloud compute today, it's a massive data center with tens of thousands of servers, if not even hundreds of thousands of servers, all acting as one, right? So as the hardware started to become available, then you started to see the whole, the software started to change. Before you had large applications which were monolithically written. Then you started to see the whole idea of Kubernetes and containers where applications actually scaled up, by scaling out, not necessarily by writing one large monolithic application, but they really were scaling out. So you started the evolution of the whole scale-out architecture. Now, if you think about the scale-out architecture, and it's hard to see it on this picture, what enabled the scale-out was effectively the network. And I will show it to you in the next few slides how network enabled the scale-out. But without the scale-out that's happened, almost all the applications that you experience today, right? Whether it is the Google search or being able to, spend a lot of your time on TikTok or social media, all the things that you shouldn't be doing but you keep doing, it's all enabled on these platforms which are all based on distributed, computing. Now, about 20 years ago or so, Oracle phrased this term, which actually Sun, my apologies, Sun phrased this term that says, network is the computer. It didn't actually make sense to me then what people meant by network is the computer. But when you actually think about it now, when you think about what the computer is, it is nothing but a whole bunch of distributed compute, all connected over a single large fabric. Then it starts to occur to you that without the network, there's no such thing as a large-scale compute. Now, there's different ways to solve this problem. Today, you hear these concepts about chiplets, right? Taking, a large chip, breaking it down into smaller pieces, and then connecting them over UCIs and other kinds of interfaces. But they can only get that big because a PCB is going to limit the size of how large a chip you can build. So if you really want to build the largest compute in the world, how are you going to do it? You have to put it over a network, right? And when you think about the size of these networks that you can build, they could be very, very large. You can easily attach about hundreds of thousands of servers in a large data center that's about the size of a football field. And over a period of time, there's a lot of networking technologies that competed to essentially be the winners. There used to be ATM, there used to be CIDI, there used to be FIDI, but over the last couple of decades, the only one Ethernet technology that continued to survive and flourish is Ethernet. Why Ethernet? It's very simple. It's open, standards-based, completely interoperable. More importantly, there's a ton of competition. Every day you look around, there's another company in the Ethernet space trying to make Ethernet networking. And all of that has essentially accelerated the pace of Ethernet innovations. Today, to give you a perspective, on an annual basis, there is 600 million Ethernet ports sold. Okay, somebody, last time I presented it, they said, well, what does it mean? What does 600 million Ethernet ports mean? There's about 150 million babies born on the planet every year. You can give them 4 Ethernet ports for everybody who's born to give you the context for what 600 million Ethernet ports means. That is how ubiquitous Ethernet is, right? When you actually think about your cars, not a long time ago, you had proprietary technologies on your car connecting all the infotainment systems, all the sensors, the data collection mechanisms, and so on and so forth. Today, it's all based on Ethernet, right? If you go to factory automations, the factory automations used to be based on proprietary technologies, all going towards Ethernet. That's how ubiquitous Ethernet is. And then you say, why is Ethernet that successful? That's because, number one, it's open, standards-based, plug and play. And more importantly, because of competition, it drives a lot of innovation. We at Broadcom are in the Ethernet business, and we can't stand still because there's so many companies competing with us in this space. So the only way we can actually be in business is to relentlessly execute, right? You innovate and you execute. And I want to give you some perspective on what this execution does or this innovation does. Over the last 10 years, every 18 months, we've doubled the bandwidth of the chips that we've put out there. Okay, and to put that into context, I know some of you here are from the service provider, businesses, and you're building large telco networks. About 10 years ago, if you went and asked somebody to give you 128 ports of 100 gig, okay, 128 ports of 100 gig, they would have given you a list price of $1 million, and it would have consumed 20,000 watts of power. Okay, 10 years ago, $1 million. 20,000 watts of power. Today, you can get 4 times the performance. Instead of 128 ports of 100 gig, you can get 512 ports of 100 gigs, okay? For less than $10,000. For everybody who's complaining about inflation, bet on Ethernet, okay? We will take care of it. So you can go from $1 million to $10,000, but more importantly, when you think about sustainability, what consumed about half a rack space and about 20,000 watts of power, today is 500 watts of power, okay? So it pays for itself to rip out all the existing networking infrastructure you have today and replacing it with the latest, because the amount of money you're going to save on power and the reduction in the carbon emissions is bar none, right? Just think about it, 99% reduction in the cost and 99% reduction in power over 10 years. And this relentless march is going to continue. We have 50 terabits today. Most people can actually predict what our roadmap is going to be 18 months from now just by looking at this slide, right? That's why Ethernet. Now, however, while Ethernet's been great for the last 10, 20 years, it's not without its set of challenges, right? When you think about cloud computing, it was all based on taking CPUs and distributing these CPUs over these large data centers. But now when you actually think about this whole idea of ML and AI, everybody talking about accelerators and GPUs, there are thousands of GPU cores on a single die. And that's not sufficient to build a large ML AI training model. You start to hear about how it takes billions of dollars to build these training models. That's because it requires tens of thousands of GPUs. Some of these clusters which are being built today, this year, are probably going to be about 32,000 GPU clusters, each having thousands of cores in them. And chances are these things are going to cost hundreds of millions of dollars to build, right? That's the amount of infrastructure that's going to get built by one company, and there's a rat race going on today for multiple of them all trying to be ahead of each other in these training models. So when you start to think about these training models that scale to the levels that we are talking about, network becomes even more of a bottleneck than it has ever been in the past. About 6 months ago, or maybe 5 months ago, Alexis from Meta presented this slide. And it basically said, the network I/O is the foundation for these new recommendation models. And this was even before generative AI started to be talked about, right? And what it shows here in these different blue charts is the different kinds of workloads. M1, M2, M3, M4, it's probably their code names for different models. Don't ask me what they are. But if you actually focus on the numbers here, what it shows you is in some cases, 57% of the time it takes to complete, whether it is a training model or an inference model, is spent in the network, right? If I told you, just to put that into perspective, you work 8 hours a day, that you're going to be spending about 60% of your time in a day, right, in the traffic every day. That's about 5 hours you're going to be spending in traffic. You won't like that. That's exactly what's going on here. That's about 50% of the time is being spent in networking, where the GPUs are waiting for the information to be traversed over the network, right? And so when you look at that and say, why? What is the problem in the network? It's not about the problem in the network, but what's happening is the GPU workloads or the AI workloads are very different from the compute workloads that we knew of before. In the case of the compute workload, it was small packets, small flows, multiple machines talking to each other. In the case of GPUs or AI machines, there's very, very large flows. What I mean by a very large flow is the communication between one GPU and another GPU lasts for a very, very long period of time. And a lot of data is being transferred between those two GPUs for a long period of time. Now imagine this. When you have very, very long communications, the best way to think about this is you're on a highway, let's say you're on the Autobahn, and you have 4 lanes, and you could go unlimited speed on all these lanes. But what if all the cars decide to stand behind just one truck in one lane, and all the remaining 3 lanes are sitting empty? What ends up happening? Everybody slows down, right? So the nature of the traffic flows in machine learning are very different than how you've seen cloud computing before, and that actually puts a whole bunch of new stress in the network, and very different than what we've seen in the past. And this picture is really what it's trying to show you, different ways that you can get stuck behind somebody else, and you get really backed up. It's like standing in the line, somebody is waiting to order something in the restaurant, and they're asking 50 questions, and you're sitting in the back sitting very, very hungry, right? That's what it feels like. The whole network is getting blocked up because you have 1 or 2 workloads that are holding everybody else up. So then you look at this and say, what can we do? And here is where I'd say just the innovations in the Ethernet are going to keep happening. Either it's going to be us, Broadcom, doing it. If you're not going to do it, somebody else is going to do it because it's open standards based, and somebody else is going to win. So what we've just actually announced yesterday was perfect timing, was this chip. It's called Jericho 3. It's hard to probably see it, but I can tell you it's pretty exciting. It's got tens of billions of transistors. And what it tries to do in this chip is address some of the problems that we've seen in the last couple of slides, is being aware of the fact that the traffic flows in an AI environment are very different, and essentially being able to build a very large cluster. Today, we can actually build a cluster that is 32,000 GPUs, each at 800 gigabits of speed. Okay? If you try to actually do the math, that's about 25 petabits of data transfer that you can actually do in a very, very large cluster. You can probably look at this and say, does somebody need it? Actually, people are calling and saying, hey, I wish we had this now, not 6 months from now, because by the time we actually get samples out, it goes to production, takes about 6 to 9 months, sometimes about a year. But that's how much demand is there for chips like this to address these problems, right? And to do that, there's a bunch of things that we do. And I'll give you, just one example of how we do it. Like I gave you the example when you're on an Autobahn, there's 4 lanes, and essentially you're all stuck behind one traffic. What we do is perfect load balancing. For example, the switch is very, very aware when looking at a communication from one GPU to another GPU and saying, look, if you want to go from GPU A to GPU B, don't take path 1, but take path 2 or path 3. So we're constantly aware of what's exactly going on in the network and making sure the network at all times is properly utilized, and you don't have a lot of underutilized infrastructure. Right? So there's a lot of innovations there. What does this all lead to? And I'm going to take a little bit of a comparison to InfiniBand. Here's what happened about InfiniBand. How many of you probably heard about InfiniBand in the past? Good number of you. And you probably are hearing about it more now than you've heard about it in the past. It was a technology that most people thought was dead. To the brilliance of NVIDIA and Jensen, he clearly identified that networking is the key to how GPUs are going to scale. So Mr. Jensen bought Mellanox. Mellanox was the only company in the world that was building InfiniBand as a technology. Now when you go to NVIDIA and try to buy a GPU system, they'll try to sell you a DGX, which is a completely vertically integrated system with InfiniBand in the backplane. What's the problem with it? The problem with it is it starts to look again like a mainframe. So we are back 50 years ago on how computers used to be sold, large mainframes. Instead, what is it that you want to do? You want to be able to build a distributed compute over a distributed open compute fabric like Ethernet. And then what will the InfiniBand guys tell you? They'll say, well, the Ethernet performance is not good enough. It sucks. Excuse me. But the reality is when you actually build these very large fabrics and look at how fast Ethernet is actually innovated and the bandwidth that's available on Ethernet, these are open benchmarks that show you that Ethernet actually achieves at least a 10 percentage performance points advantage over InfiniBand. Now, for most people, you say, hey, 10% is not big enough for me to sway my decision one way or the other. But let me actually give you some perspective. When you build a 32,000 cluster, you're probably spending at least $1 billion on that cluster, 32,000K cluster. It's about $1 billion. The cost of the networking is less than 10% of that, okay? So if I can make your $1 billion infrastructure 10% more efficient, the network actually pays for itself. This is what I call infinite returns on investment, because anytime you put some amount of money, immediately you get your money back, and you can do it every day, every other day. That's a lot of return back, and that's exactly what Ethernet gives you, which is it cuts the cost of the infrastructure by improving your efficiency by at least 10%. It's open, and if you don't like what we do on Ethernet, go buy it from somebody else. It's not just a single vendor that's making Ethernet available. There's a lot of competition in Ethernet. So what I'd like to leave you with is, if you're thinking about building anything which is HPC or an MLAI infrastructure, please ask the question, why not Ethernet? Or forever, you will be stuck with a vertically integrated solution, right? Now, as we're doing this, obviously, we're doing this all with sustainability in mind. As I've given you an example, 10 years to now, 99% reduction in power, 99% reduction in cost. But even between our two generations, 18 months ago to now, we have a 40% reduction in power between the previous version of Jericho chip that I have in my hand and the one that we currently have. Not only that, some other data points I want to share with you. About 10 years ago, if you wanted to go buy an Ethernet switch or a router, you paid about $1,000 for a gigabit Ethernet port, and you paid about $100 for a gigabit Ethernet optic, especially for those of you who are in the telco market probably realize that. And what used to happen, the networking OEMs would give you a pluggable Ethernet optic for free if you bought their switch. Today, actually, the math is inverted. You can go buy a 100 gigabit Ethernet port, at the silicon level at least, roughly around $10 a port. Okay, $10 a port for a 100 gigabit Ethernet port. But if you try to buy the optic is about $100. So actually the math has inverted, where the switch used to be 10 times the cost of the optics. Today the optics are 10 times the cost of the switch. Why? Because the switches took advantage of Moore's law, and you rode the price benefits of cost reductions by successively going to the next node. But optics never never took advantage of silicon capabilities. They're always manufactured manually, right? So because of that, today optics are one of the largest costs in building a large-scale computer system, in being able to connect all of these things. So a lot of what we are focusing on the Ethernet is, how do you avoid going to optics? Can you actually get more and more mileage out of the copper? Okay, that's one. Two, if you have to use optics, can you reduce the active components in the optics, which is, can you reduce a lot of the DSPs and try to go as fewer components as possible? And number three, if you can't do one and two, the other thing that you could do is, why don't you bring the economics of silicon into optics, and that's called silicon photonics. So a lot of what's happening in the Ethernet space in terms of innovation is, one, try to extend the reach of copper. Two, if you have to use optics, reduce the DSPs which are used in optics. Number three, if you have to use optics, then try to see if you can get the benefits of silicon photonics, right? So a lot of this work is going on. That's actually another area of advantage for Ethernet versus InfiniBand. You try to buy InfiniBand, they limit the cables that you can buy, the distance of these cables, who can sell those cables, and what they charge for the cables, right? All of this, again, you want to be on an open ecosystem. So to that, we're very, very thankful for what OCP does in being able to provide the platform for technologies like Ethernet to be able to flourish. We have made contributions to OCP over the last many years, starting with our chips like Tomahawk 5, specs that we have submitted for how you build very large-scale routing topologies, and most recently how you build systems using the Jericho 3 chipset. So thank you very much for your time. I appreciate your interest in Ethernet, I would say, and I would leave you with the following, which is the largest compute systems in the world are being built with Ethernet. So as you look forward, thinking about deploying anything which is ML, AI, GPUs, and accelerators, please ask the question, why not Ethernet? And do not get caught up in proprietary InfiniBand technologies. Thank you.
Please welcome QDeep Tech's CEO, Dr. Angie Carey.
Good morning, everybody. I hope you can hear me. So today I will speak about an exciting topic, which is quantum computing. And actually, what is quantum computing? Why at all quantum computing? And what is it good for? So basically, quantum computing is all these devices that you see here. We'll come at the end of the talk to these devices. But what is at all a quantum computer? So quantum computer or quantum computing is a cross-technological and cross-scientific technology in the intersection of physics, computer science, and mathematics, which actually take advantage of quantum mechanics phenomena, like, for example, superposition, randomness, intrinsic randomness, and entanglement. And by being able to manipulate a single quantum system and control it very well, wants to process information. So this is the definition of quantum computing. And as you know, by classical computation, we process information through bits, that is 0 and 1s, and we get either 0 or either 1 in the response. By probabilistic computation, we fluctuate between 0 and 1s with different probability distributions, so we get fluctuation between 0 and 1s, and this is still two classical bits that fluctuate. And quantum computing, it gets actually advantage of superposition. These balls actually, they should be spheres, but this is not our quantum compression, is the compression of Google Drives when I pass the slides. And in this quantum world, the 0 and 1 is in a superposition, which it means one qubit actually can process information with different amplitudes, which is written A1 and A2 here. So these amplitudes are the probability distribution at the same time. So normally in the media, you see this presentation as a sphere, should be a sphere here, or it is the Bloch sphere, or the famous Schrödinger cat, when you say that the cat is dead and alive, which is a wrong language because the cat is in a superposition or has the probability of being dead and alive at the same time. So this is what we leverage for processing information. So now if you add 2 qubits or more classical bits, as you see, you get a certain advantage because in the classical way of computation, you will encode your information in a bit strings, and you actually will have 1 out of 2 to the n possible permutation. In the quantum computation, through the superposition, you will get all the possible superposition states 2 to the n processed at the same time. So now the question is, but if I actually put these things in the superposition, then what I have? I just have n qubit linearly adding up. And then I go to probabilistic classical computation, which everybody is confusing what is better, quantum or probabilistic. So this will not give you anything, basically. What you want to do, you want to entangle these qubits. And this is the power. You actually process the information in an entangled superposition state, and this entanglement is nothing else as a kind of computational multiplier of all these qubits that live in this space in such a way, actually, that you will get an exponential, you will process the information, and you might get an exponential speed up in comparison with if you get just linear classical qubits and add them one to the another. And this is this famous entanglement, and this is what Einstein didn't accepting and say this is a spooky action at the distance. We are not going to explain physics now, just to give you that this is the crucial part, this entanglement, because the input state is in an entangled superposition of all these qubits, and this gives this exponential advantage. So this is our quantum computer. This is all. We have all the possible probability space, and we process the information in this infinite probability space, and basically we want to liberate some advantage. But we humans, we cannot actually understand anything from this probabilistic space. It even lives in a kind of Hilbert space which we cannot even understand. So we are classical, we want to see an output. So we need to measure. At the moment that we measure from all the probability space, we actually get one n-bit string output, which is randomly sampled from all our possible probabilistic way of processing the information. And now you will tell me, okay, hang on, so you did all of this just to get an n-bit string that randomly sampled that probably will give you also the wrong answer. So what the heck is with this quantum computing? So there should be something more than just measuring and getting one n-bit string randomly sampled. And this something more is exactly the core of quantum computer, that it's actually the ability to program and these amplitudes in such a way that you will boost or reinforce the amplitude of the correct answer by suppressing the amplitudes of the wrong answer. And the core of this is exactly this entangled superposition that we have, what is called disruptive interference. So it's not just doing random sampling or random computation. So basically, does it work for the whole problems? Are we going basically to solve all the problems of the world? Because this is how is solved quantum computing. And no, the answer is no. The art of quantum computation is exactly to find these classes of problems where this process of programmability takes you a kind of advantage in the computation, being it exponential or quadratic or whatever, and this is what is claimed quantum advantage, quantum supremacy, or quantum speed up. So it doesn't work for all the problems of the universe, whatever the hype that the media is selling out there. So we need to find these problems that we get a quantum advantage. So now, why quantum computing? This is all what was quantum computing, nothing more, yeah? So now, why actually we need this quantum computer, and what is it good for? So the first reason is hardware reason. So as was said previously, we know that the Moore law is becoming very difficult and expensive, and we want to boost the power and the performance of computation, and we are coming to a kind of threshold limit, yeah? So basically, by squeezing more and more transistor in a small space, we end up in a case that quantum effects start interfering with our electronics. So we basically cannot scale more and more transistor in a little space. But why actually from the beginning we wanted to put more transistors in a space? Because we said as the surface is smaller, then basically you can do computation faster, because if something is smaller, then you can do faster computation. But then we ended up that we forgot about the leakage of the voltage. Sorry, guys. So we forgot about the leakage of the voltage, and we ended up with a power wall where we cannot do higher frequency. From 2006, we are around 4 to 6 gigahertz, and we cannot speed up this computation. Even if we go to parallel computation, we are actually in the limit of how fast can we go with the performances. And this is synchronization. This has its own problems, all the parallelization. So a study showed that there are different ways in order to scale up, to push our performances and power. And one of these ways is quantum that sits over here. There are other ways to do it, and quantum computing is one of the ways. So this is one of the reasons, is hardware reason. The second is, as you see, computation complexity. So what I show here is, if I have 63 qubits, they are, in comparison with bits, are like 10 to the 18 bits. It's missing a power 18 here. They need 1 exabyte of memory in comparison with classical computation. And I need 100 years to run a computation in a classical world when I have only 63 qubits in the quantum computing. And if I go to 1,000 qubits, I actually end up with this time to run computation when the age of the universe is 30 billion years, it's 10 to the 10. So this is the second reason why the world is thrown in this quantum computation. And from the same reason of computation complexity is actually the time and space that is required to solve a problem. Basically, it was shown that there exists some faster quantum algorithms that can solve problems that are not solvable in the classical computer. So this cycle here, it's called P-complexity classes, means here lies all the problems that you can solve in a classical computer in a polynomial time. Polynomial time means the time that is normal to solve a problem, not the time of the universe, or that the problem doesn't scale exponentially with the input as you increase the input data set. So then they found that we can have some quantum algorithms that can solve problems that lie outside of this cycle, and this gives kind of a kind of boost. Let's try to build such a computer because we might discover more problems that they are hard for classical computation and solve them in a quantum computer. So a second reason is a specific simulation, unique simulation that the native language of these simulations is quantum. For example, quantum chemistry. You can simulate them classically, but you cut all the correlations and you cut many, many things. And exactly this managing this complexity gave birth to these algorithms. And let's go who were these algorithms. Like the first one was a Shor algorithm, which actually showed an exponential speed up in order to factorize a large prime number. And factorization of a large prime number actually gives you the threats to the existing internet security, which is asymmetric encryption. The same, we have the D-log algorithm that is also showed Peter Shor. It's also an exponential speed up, which also is a threat for the cybersecurity. And there was a Grover algorithm that has a quadratic speed up that actually it's a brute force attack for the symmetric encryption. So from all of this, it was a reason to build a quantum computer. But one reason that is never spoken is the energy as a computational resources. Because actually what Landau said that information is physical, which it means each time that you do a computation in an irreversible way, which some of our logical gates, they are irreversible, then you actually dissipate energy. And by this, every time that you erase one bit in your logical computation, you dissipate energy. And this is the Landau limit, how far we can go with the energy dissipation. This is some targeted systems to get close to this Landau limit, and this is all our benchmark systems that we work now. And by 2000, okay, let's take it 14, we see that the energy that we need for computation actually exceeds the world's energy production. And then what you do with it? Or you change all your computation to reversible logics, that you can do it classically, or you find a computation that processes the information in a reversible way. And quantum computing is a reversible way of computation because Schrödinger's equation, they are reversible in itself. So this is the third reason why the world is thrown towards this quantum computation. And The difference now that why quantum computing is different also from classical is that physically we don't have only silicon and transistors. There are many, many ways to build quantum computers. There are artificial atoms, so superconducting circuit. There are atom, ion, molecules. We have photons, light. We can build quantum computers with light or some topological quantum computers. Another difference is that we have different computational models. We don't do only gate models. We have what is called adiabatic computation. We have one-way cluster states, and we have hybrid computations where different models. Who is going to win? We still do not know. There are the quantum computer that will solve all these problems is the famous universal quantum computer that still needs a fault-tolerant technology for error correction. Because the quantum is very noisy, when it interacts with the environments, it basically gets destroyed. So this is what is holding quantum computing, the scalability. There are existing quantum computers, near the noisy intermediate quantum computers, and there are non-universal quantum computers, like adiabatic quantum computers that are, or for example, annihilers, that they are used for optimization problems. That is the next talk behind me with a specific use case, how they do these kind of things. And there are companies that working, everybody has adopted his own platform, physical platform, and his own way of computation. This is a very, very high-level architecture of how this quantum computer should get integrated. It's a huge effort from classical quantum physical layer and logical gates. And this is all what is the field of quantum computers. And thank you very much for your attention. Here you can see the Google or the IBM superconducting computers. Here is the annihilator, this specific case optimizer, which is in the market. And here is the chip of the photonic quantum computer that might bring us millions of qubits by 2026, as it promised. Thank you very much.
Please welcome Chairman of the ORAN Alliance and Deutsche Telekom's Senior Vice President, Group Technology, Dr. Alex Choi.
By the way, thank you, Angie, for her nice presentation. It's a perfect segue. So, first of all, good morning, everyone, and I'm so happy to be here today to talk about the telco use cases, which is a practical use cases. You can already get the very encouraging results. So, due to the time constraints, right, let's directly jump into. Yes, and also, I have my second title, which is the chairman of the ORAN Alliance. I don't know if you're familiar with that. Where's the clicker? Yep. So let's just start with this picture. So now you might already seen this fancy diagram, so I don't need to talk too much about it. Angie, the previous speaker, has done a fantastic job. So let's go to the next slide. It's an optimization problem that I'm talking about. So optimization problem areas, especially the combinatorial optimizations, are classified into process optimizations and network optimization, quantum network, industry 4.0 use cases, as shown on the left-hand side. The problem area that I talk about today is called automatic cell planning for as a telco use cases, as colored. And this part is already covered by Angie, the previous speaker, so I don't need to spend time to talk about it and jump directly into the Deutsche Telekom telco specific use case. It's called automatic cell planning. So one of the crucial tasks within the optimization of modern radio access network is the optimal cell site selections, which turn out to be a non-polynomial combinatorial optimizations problem. And with Deutsche Telekom, our best mobile task team is facing this challenging problem, and it's called automatic cell planning. And here are the situations as shown in this chart. And first, the amount of radio cells will dramatically increase, for example, way beyond the hundreds of thousands. And second, many constraining factors are there, and also many antenna parameters and complex cell-to-cell interdependency makes the site selection problem extremely complex and challenging. Besides, the proper initial site selection and cell planning together with the continuous tuning of the antenna parameters are essentials. So the task team is looking for future-proof approaches that can manage this growing complexity. So my team in Berlin, the task given to my team was to analyze the potential of digital annealing in the context of this optimal site selection problems and conduct benchmarking studies. So now let me describe the more detailed steps to search for the solution to this site selection problem. As demand for mobile connectivity continues to grow, the need for additional sites to improve the coverage and the service quality became increasingly important. However, the site selection process is extremely complex with a range of data and constraints to be considered, including evaluation pixels. Pixel means 20 by 20 meter squares areas, and the antenna azimuths and existing fixed sites and candidate sites. So to address these challenges, we use the quadratic unconstrained binary optimization model, in short QUBO, and this model was developed. And the model is designed to optimize the weighted mix between coverage and service quality for users with the aim of minimizing the interference effects. And this model is shown in the middle on the right-hand side. It's unreadable, it's too small, but anyway, it gives you ideas about this model. This quadratic unconstrained binary optimization, QUBO, is a mathematical model used in optimization problems where the goal is to find the values of binary variables that minimize the quadratic objective function subject to linear constraints. In quantum algorithm, QUBO is used to formulate combinatorial optimization problems as a problem of finding the ground state of quantum systems. So this can be done using quantum annealing, a type of quantum computing that leverages the principles of simulated annealing to find the optimal solution to the QUBO problem. In the context of telco network cell planning, this QUBO model can be used to optimize the placement of the cell towers or cell sites, and with the goal of minimizing interferences and maximizing coverages while adhering to the various constraints. By formulating the problem as a QUBO model, it can be solved more efficiently and accurately than with the classical optimization method. To test the effectiveness of the model, a benchmarking study was conducted by my team between our DT internal solutions and the digital annealers developed by Fujitsu. The study focused on two key performance indicators. One is total execution time, and the other one is optimization scores, in other words, error rate. The Fujitsu digital annealer is a specialized computer that's designed to solve complex optimization problems quickly and also effectively. It's based on a technology called simulated annealing. Angie briefly mentioned it, which is a method for finding the optimal solution to a problem by gradually cooling a system like a matter and allowing it to settle into low energy states. The quantum computers in early stage are not yet able to benefit from advances in quantum algorithm, as you may know. So the issue is known as it's called the chain break, and it arises in quantum annealers, whereby the problem breaks down as the scale increase, so which leads to a suboptimal solutions or errors. To obtain accurate result for a problem, the quantum bits or qubit must maintain their quantum state free from external interference, such as cosmic or magnetic rays. And if this condition is not met, the qubit lose their entangled state and cannot perform calculations anymore. So the delicate nature of these quantum states result in very frequent errors, necessitating the need of the error corrections. And although noise is less of a concern for the quantum annealers due to their adiabatic analog processes, but still the sparse connectivities between the physical qubit means that the logical qubit must be represented by a set of physical qubits. And typically, a fully connected logical qubit requires around 30 to 80 physical qubits. The digital annealer works by encoding the problem as a spin glass or Ising model, which is a type of mathematical models that represent the interactions between variables. It then uses simulated annealing algorithms to explore the possible solutions and find the best one. And the key advantages is its speed. And our results show that the digital annealer was able to outperform our company's internal tools in both KPIs, performance, the better optimization result with a less error rate. So this is possible because the digital annealer design features a fully connected architectures, and that enables to solve the complex combinatorial optimization problem at very, very rapid pace. Moreover, it is able to achieve a greater accuracy than quantum annealing, which has limited qubit connections, and this is a result. Evaluation results. This slide shows the result of our simulations. As you can see from the table below, we compare the performance in two cases, one with a 60-degree of antenna angles and the other one 10-degree antenna angles. So in the first row of the table, this is a case of 60-degree antenna angle, and we found that it performed 37 times faster than the traditional computing. Moreover, the solution quality error also improved by about 40%. And this is an excellent result, especially since the telecom companies very openly perform this kind of a cell planning program on a national scales, and the configuration parameter range it's vast. And this means we have to, we are running this program over and over. So the more times you run it, the more speed gain or time gain you achieve, with this digital annealers. So obtaining the result more than 30 times, or exactly 37 times faster than is a significant improvement, and it gives a very enhanced productivity. And moving on to the second case in the table, which was deliberately included to find the characteristics of the digital annealer. And this is the case of 10 degree, and we found the degree of speed improvement is not as impressive as the first simulation case. So this finding highlights the importance of understanding of characteristics of these annealers to obtain the best performance. Otherwise, you may not get a good performance. So by understanding and utilizing the characteristics of the digital annealers, users can achieve remarkable performance improvements. Our result already showed that this annealer was able to outperform our DT internal solutions, and this demonstrates a potential for the quantum computing for our daily business, which is a site selection and optimizations. So that leads me to this chart. This is our DT, Deutsche Telekom, and T-Systems Quantum as a service. So I want to share some insights with you today. So our offering, it's called the Quantum Cloud, is designed to be a quantum computing agnostic, which means it can work with the various quantum computing technologies and platforms. And the Quantum Cloud we are offering is a unified access platform, which simplifies the process for enterprises to tap into quantum computing resources, and this makes it a lot easier for business to explore and experiment with quantum computing without having to invest heavily in their own infrastructures, quantum computing infrastructures. In addition, our T-Systems also provide a range of additional services to help enterprise get the most out of their quantum computing journeys. This includes consultancy and training and educations and integration and support. So, and also customized solutions. In a nutshell, Deutsche Telekom T-Systems quantum services are designed to help the enterprise unlock the immense potential of quantum computing by offering a comprehensive and a flexible suite of solutions that cater to a wide range of business models, business needs. Lastly, our company has announced last month that T-System will provide their customers with the cloud-based access to IBM's 127-qubit Eagle quantum processors. Finally, takeaways: the true quantum computers are showing promising results up to a certain degree of complexity. However, as of now, they rarely outperform the classical computers in optimization problem, and this is a problem. So when it comes to the automatic cell planning, we've seen real benefits, not by using the true quantum computers, but by using a digital annealing solutions. And this is definitely a step in the right directions until we see fully, full-fledged true quantum computings commercially available in the market. So our experiment with Hojit's digital annealer has given us truly encouraging results, and it's very exciting to see the potential of quantum computing, to be precise, quantum-inspired computing. Yeah. In summary, we are witnessing some exciting advancements in the world of quantum computing, particularly in a combinatorial optimization problem, and in telco cases, we have many such problems already. So while there is still work to be done, the progress we are making is truly inspiring, and we will keep pushing the boundaries and exploring new possibilities as we venture deeper into the quantum computing landscapes. This is it. Thank you for your attention.
Please welcome Ampere's Vice President of Products, Madhu Rangarajan.
All right, good morning, folks. I'm excited to be here. I've been in the server industry for over 23 years now, and I've not been more excited, and I've never had more fun than I'm having right now as part of Ampere, and there's a reason for that. And that's because we have done something revolutionary. We have created a cloud-native processor for the first time, and it's a processor that's specifically designed from the ground up for cloud-native workloads. And what we mean by that is these are containerized scale-out workloads deployed in a scale-out manner. And these are workloads in the cloud that are pretty common, things like web, memcache, scale-out databases, AI inference, transcoding, and so on. And on all of these workloads, we are delivering performance and efficiency with no compromise. And now, why does this matter? and you heard a few talks earlier talking about the carbon footprint and the effects of that. And data centers are contributing a significant portion of the global CO2 footprint now. And this continues to rise with the rapid growth in cloud. And one thing that really surprised me was that the emissions from data centers are actually higher than emissions even from some of the industries that you typically associate with carbon footprints, like aviation and shipping. So it's really critical for data center operators to take this into account as they plan their build-outs and navigate various government regulations that look to curb this footprint. And just as an example, in Ireland, data centers have been projected to use nearly 30% of the power in the country by 2029. And that's more power than all of the rural homes in Ireland combined. And what this is doing is it's forcing calls for moratoriums, and it's actually leading to delays where multiple major players have made decisions to delay build-outs because of the power shortage. And these regulations and challenges are only expected to continue to grow, and this is going to force cloud service providers to figure out how to deliver more with less. And on top of that, there are power shortages globally, and even more so in Europe, where power shortages are forcing really tough choices. Just one example, there's a neighborhood in East London with multiple data centers. There's also a critical shortage of housing there. And they're unable to build any more houses there because all of the power there has been taken up by the data centers. And in addition to that, power costs have actually increased by 200 to 300% since 2021 in Europe for obvious reasons. And this has a really large impact on the bottom line of cloud service providers, since, as many of you no doubt know, power represents a pretty large portion of the total cost of ownership of servers. And that is what makes this new paradigm of cloud-native computing, and specifically the cloud-native processors that Ampere is building, extremely critical. Every few decades, a new usage model comes along, and it drives a shift in the dominant software model. And that change in software happens first, and once the software reaches a tipping point, the hardware catches up. This has happened in the past. There was a transition from mainframe computers to a client-server model, which led in a transition from the old mainframe hardware to the heyday of the x86 hardware. But now there's a new transition that's already happened in software, and that is the cloud model, where your workloads are no longer monolithic. You no longer have a single mail server and a single file server and things like that. It's a cloud-native model where you have containers with all of the workloads I spoke about earlier deployed in a scale-out manner. And that's the software has already shifted to that model, and we are already at a tipping point where large portions of the software world have adopted this model, and now it is time for hardware to catch up. And this is where Ampere's revolutionary cloud-native processors come in. They can serve this usage model far more efficiently than legacy hardware, because the legacy hardware is still based on the previous client-server paradigm. And at the end of the day, cloud service providers want as much capacity as possible in a given footprint. And this new paradigm allows them to do that. This chart is busy. I won't dwell on it, but it's from luminaries in the computer architecture world, Drs. Hennessy and Patterson. Many of you have no doubt had courses with textbooks written by them in college. And what this shows is a period of time when we had Dennard scaling. We'd regularly get 2x performance on every core every 18 months, and the cost would go down. And life was good because everything would just be 2x faster without any refactoring. But those days ended sometime in the early 2000s, and the architectures had to make incremental shifts where they had to start going multi-core. They were still focused on some of the legacy metrics like, okay, single core performance and so on. But that's when the software world also started making a transition to the scale-out model, because the software developers quickly realized that, wait, I'm not getting 2x performance without doing anything. I actually need to refactor the software. And that's exactly what happened with the legacy, it's new software running on legacy hardware. But the new software doesn't care about the same metrics that the legacy hardware cared about, right? It's no longer about localized metrics like performance per core or even on a single server. What the cloud world cares about is metrics at an overall fleet level and a data center level. And it's time now for the hardware to catch up and adapt to this new world and optimize to those metrics. And this is where you enter Ampere's cloud-native architecture. What we've done is we've moved away from some of the legacy features that were largely driven from client. Things like turbo and hyperthreading introduce a lot of unpredictability in workload performance and performance jitter. So instead, what we did is we designed a large number of high-performance general-purpose cores that operate at a consistent frequency. And they also have single threads with dedicated resources, and they deliver consistent performance. And in addition to that, we are focused on general-purpose performance for the type of workloads I spoke about earlier, web, memcache, databases, and so on. So we don't add lots of power and area for dedicated acceleration features that take up a lot of power and area and only benefit certain small subsegments of the market. And by doing all of these things, what we can do is we can deliver twice the performance at half the power. And not only that, we can do that by pushing the utilization of your server to over 80 to 90% with linear scaling and performance without any performance jitter or any of the other artifacts you might see on the legacy processors. And what this allows us to do is it allows us to deliver a massive lead over competition on a key metric that matters to the cloud, performance per rack. Now, performance per rack is a really powerful metric because it encompasses three different things. It encompasses power efficiency, it encompasses real estate footprint, and it encompasses performance. And it speaks directly to how much capacity a cloud service provider can deliver with a constrained data center power and area footprint. It tells the cloud service provider how many customers they can serve and how much revenue they can generate within a given footprint. And as shown here, Ampere allows you to generate 2.5 times more performance per rack on most general purpose workloads versus the legacy x86 competition. And as you can see, right, we're not talking about incremental numbers here. We're really talking about a massive improvement here, and it speaks to the fact that we really are in a new era of computing. And this is true no matter what your rack budget is or what kind of data center you run, whether it's a large hyperscale data center or a small regional data center or even a very constrained edge location. In all of these cases, Ampere allows you to do a lot more with less power and less area. And deploying our architecture not only means that the planet will thank you, but so will your balance sheet as you look at the revolutionary performance, power, and area advantages that are delivered. And once again, right, if you look at these numbers, we're not talking about incrementally better numbers. These are really massive advantages that come with Ampere's cloud-native processors. But again, doing these revolutionary things, it's not us alone. It takes a community of you and OCP, and we are very proud of our association with OCP. We have contributed both of our reference systems so far to OCP. In 2021, we contributed our Mount Jade platform, which was for the Ampere Ultra processor. 2022, we contributed Mount Mitchell, which is for our upcoming Ampere 1 processor. In 2023, we joined the DCMHS work group. And we're really looking forward to our future contributions on things like OpenEdge, DCMHS, DCSCM, and so on, because all of these build upon the sustainability story I was talking about by modularizing the server and making significant portions reusable. And we also continue to contribute to the open source firmware world, since all of this allows the ecosystem to adopt our technology much more easily and more importantly, allows the ecosystem to innovate on top of our technology. And this allows the world to design with our revolutionary cloud-native processors. And what we like to say is less power is the new power. The paradigm has changed. The foundational model has changed from scale up to scale out. And shifting to this new type of hardware minimizes all of your carbon footprint. And I'm not talking just about the operating carbon footprint. There is also the embodied carbon footprint. There is all of the footprint that comes with building out the data centers, all of the concrete, all of the other non-server stuff that goes with your data center. It minimizes all of that footprint as well. And my call to action is to ask you all to look through all the resources we have available to begin your journey with us. There are a ton of resources. We do a lot of work to make sure that over 140 pieces of software are regressed every night, and the top of the tree is building. We have solution stacks available. We have links to our various partners, some of whom are in the audience. So all of those will help you get started on this journey with us. And do visit us and our partner booths as well. As you can see, we have our partner booths. We have the Ampere booth. We have our awesome colleagues like Sean Warley, who's going to give a couple of talks on his own. And he's also going to be talking with Peter Groth from HPE. Jayesh is going to he's going to get much deeper into one of our platforms called Mount Bonnell. And so it's all going to be exciting. And we were really looking forward to having all of you come to join this journey with us. And thank you so much, and appreciate all of your time, and thank you for listening to us.
Please welcome back George Chaparian.
Hello again. Before I introduce our next keynote speaker from Amazon AWS, I want to set something in context. This morning we announced the specification of what AWS has done, doing, and why this is important for OCP and their collaboration with OCP, and also for the industry. Currently, we have a portfolio of product in OpenEdge server for mobile edge. And also we have introduced, as you know, from the Global Summit last year, open data center, modularized, edge for servers as well. What AWS has done with us, through us, is bringing in now another piece of the puzzle for making sure that the near, mid, and far edge portfolio that we have to help the community in the edge technology forward. And this is, we call it open edge, open enterprise edge. And this is where OCP is going to work with you guys and with Amazon's help to expand multi-vendor open edge for enterprises, for our ecosystem. So without further ado, let me introduce Michael Lane. Michael is the Principal Technical Program Manager from Amazon. Michael, welcome.
Thank you, George.
So we're going to do this interactively. So Michael, please tell me how Amazon has taken this journey to come to this point.
Well, Amazon started many years ago, as a retail business. But then we quickly moved to the cloud business. And in 2006, AWS started on its first journey with its S3 offering. It's the simple storage services. And then 5 years later, networking caught up, and we did our first disaggregated network, Ethernet-based, with our own NOS. 5 years later again, in the retail business, we opened up our first frictionless store, Amazon Go. Again, another 5 years later, We changed our way of thinking in terms of networking, and we implemented a disaggregated network, leveraging Dent, which is an open source operating system and network hardware. And then now, we're looking at what's next. We're looking at a converged network system.
It seems like we, OCP, and Amazon have some same kind of converging vision. So can you tell us how you are navigating this whole overview and outlook of Amazon networking in Amazon?
Let's start first with the tenets. So as with any great organization, you have some tenets you need to start with. First of all, security. Security is of the utmost importance to Amazon. Managing customers' data and customer trust is truly important to Amazon. Secondly is availability. We know inherently that the internet just isn't reliable. So we need to figure out how we do that, how we accomplish a more reliable network. Scale. In the physical stores business, we need to be able to scale to hundreds of stores. Controlling our own destiny. So this is an interesting one where we really want to go through leading innovation to be able to control our own destiny. And we thought leveraging open source was the best way to do that. And then finally, cost or frugality. One of the big challenges we have about frugality is optimizing for the long term, and when needed, making some short-term decisions that don't prevent us from that long-term goal.
I see. So tell us, please, again, what you're trying to solve. What are the problems that exactly you're trying to focus here today as an example?
Let me give you an example. So the current state today, especially in the enterprise or even in the retail network, is there are no standards in the enterprise edge. And one of the things it requires, let's take, for example, our physical stores. The physical stores have, just for its network, we have to think about the WAN. We have to think about the LAN. We have to think about backing connectivity and any type of local compute as well. The other thing about the enterprise space is that it becomes a bit chaotic. And for us, when you're having all these different types of devices connecting to your network, we need to really think hard about how we can simplify and creating an ecosystem that is far less complex.
Okay, then could you share with us, with the audience, an example of it?
Sure. So let's take a physical store, for example. In the physical stores, we have, the network has to support all of the cameras. So we have multitude of cameras. We have these labels, we call them ESLs, or electronic shelf labels, that goes on every single shelf for every single device, or in this case, every single product. Then we have thousands of sensors, we have point-of-sale machines, and this can be in stores anywhere from 200 square feet all the way up to our large grocery stores, which is about 40,000 square feet. The retail business is driving these requirements for the enterprise.
All right, then tell us from a technology point of view, what are some of the drivers in terms of deep down technology for the edge today?
So, again, going back to the retail business, if you take a look at the AI and ML workloads, a lot of those are around camera inference. So when we're tracking an object that is picked up off of a shelf, well, who does that, right? So we're starting to see more and more edge devices, whether they be inference machines, they could be embedded into our hardware, into our networking hardware. This requires a lot of automation, and a lot of rapidly evolving network capabilities are needed.
And that's why, we in OCP see this, that hardware and software coexistence and hardware and software co-design, it's really going to drive the future. That is why we also announced a very good alliance with Linux Foundation. And OCP is not just becoming only hardware organization. We are expanding a little bit into the stack, and we're looking at the link layer as well and bringing some software inside OCP. So tell us, what are you doing about it from a Amazon point of view?
Well, I'm glad you asked. So if you take a look at this, we're trying to put together all the little pieces So you have open communities like Linux Foundation and OCP. You have AWS participating in both. Physical stores, which is the division that I represent. And then you have a talented team across, in a talented community, all coming together.
Yeah, this is really great, and this is where, when my opening remark before I introduce Michael is that we are seeing this collaboration and pushing this kind of a enterprise, edge innovation into the marketplace, and also through you, hopefully, and through our supply chain expanded. So, Michael, tell us the good news.
So, Amazon is proud to announce our very first contribution to OCP, which is the Enterprise Edge Gateway.
I think we need.
Thanks, Gary.
Thank you.
The Enterprise Edge Gateway is an edge device that interconnects the WAN, the wide area network, with the local area network, allowing us to also perform capabilities such as SASE and SD-WAN functionality, which includes ZTP, zero-touch provisioning, firewalling, secure web gateway, antivirus, and even local caching. Local caching is an interesting one because as we see all these devices, these IoT devices, in our stores, rather than getting updated firmware from the cloud, that can all be done locally. From a hardware perspective, thanks. From a hardware perspective, we're leveraging standard rack-mountable device, in this case, a 19-inch 1RU device, with up to 48 ports of multi-gig Ethernet, so that supports either 1 gig or 2.5 gig, as well as 4 SFP ports that support 10 or 25 gig. We're looking specifically at a modular design because we feel that it allows users to expand as they go. It'll support Power over Ethernet, PoE, a CommE board that could be either ARM-based or it could be x86-based, Wi-Fi and LTE or 5G capabilities. All of these are supported under an open baseboard management or BMC controller, which is optional, as well as the standard security management under the OCP standards.
All right, now let's talk a little bit about software.
So obviously, there's this marriage between hardware and software that has to occur. So again, Amazon has been working very closely with the Linux Foundation on its contributions to DINT. But now we've seen that SI, this is the switch abstraction interface, has been a really important part to become more open and more standard. OCP's SI, which is commonly used in operating systems like FBOSS, and Sonic is going to be soon adopted in DINT as well. Some of the things that we really want to focus on there is the enterprise features. In the past, SI has been really focused on hyperscale features, and now we want to dip our toes into the waters a bit and focus on the enterprise.
That's wonderful. This is also, personally, for me, this is a great convergence because in my previous job, we were pushing this. Thank you, Michael, and AWS for making this happen. So when can I get my hands into this?
So a couple of things we've done so far. We've done the first step of creating this base specification. So the base specification has already been uploaded to the OCP website, so any ODM can download it. We've also started working with the SI community, and you'll have a talk a little bit later today, actually tomorrow afternoon, on Amazon's contributions to SI. And then the other thing we're working with is a number of technology innovation partners, including ODMs, key ODMs, to actually build the design package. And we expect that the design packages should be arriving probably within the next 12 months or so.
All right. This is great, Michael. We really appreciate it. Thank you for being here. So I want to also come back to conclude this with a call for action. We already see a lot of our members, about 6 of them. You can see their names here from Wistron, Celestica, EdgeCore, Delta Networks, and Brazil Networks. All of them are embracing this and starting to build their ecosystem, their supply chain. So we encourage you to come in, get the specification, and start going. This is really great because it's a disaggregated hardware. It fits exactly where OCP wants to go. And also, it's very flexible from software point of view, which you can come in with, Sonic, if you've been part of the Sonic, movement, and enhance with your application on top of it, or Dent, and you can do that with our alliances with Linux Foundation. If you want to come in and be part of the SI, enhancement inside OCP, you can do that. So we encourage you to embrace this. It is a great movement in completing our, enterprise connectivity, and also making sure that we have pushing the enterprise ecosystem at the edge. Thank you, Michael, very much for your contribution. We really appreciate it. And I just want to make sure also encourage you, tomorrow there will be an engineering workshop. We are calling it Living at the Edge of Open Networking. Encourage you to attend that. I think it will be very, very informative and very exciting. Again, thank you very much. Really appreciate it.
Thank you. Thanks.
Please welcome Google's Vice President of Engineering, Data Center, Advanced Technology Innovation, J.P. Clausen.
Hello, everybody. I hope you can hear me. Welcome to this OCP conference here in Prague. I'm very pleased to be here today. I'm excited also to share, on behalf of Google, how we drive the next generation of net zero at scale. So a little bit about myself. My name is Jens Peter Clausen, go by the name JP. I have a background in engineering and also within leadership, and specifically around innovation when it comes to technology. So I have an MBA, which I'm very proud about, because it actually gave me some opportunities to think about how you actually innovate in big enterprises. I were fortunate to work with some of the big brand companies like Lego, Tesla, and now at Google. So I'm relatively new to the industry, so I'm also here to build network. I'm excited to be here and share our story. So first, everybody knows that the mission of Google is to organize the world's information and make it universally accessible for everyone. We also want to become net zero at scale, and that means by 2030, we want everything to be net zero. The agenda today is how we actually are going to do this. It's of course not coming without any challenges when we talk about an hour-to-hour basis of being net zero. It's so much more difficult than thinking about offsetting your carbon as generally. Also, I'm going to talk a little bit more about the 3 scope of emissions and how we actually are providing some few examples of that. And then we want to make sure that we are collaborating in the industry, specifically also about OCP, and continue the journey of contribution. So first, about our commitment to make sure that our services are reliable for all users and customers around the world, and ensure that this is requiring a lot of clean energy to do so. So if we think about Google specifically, we are one of the cleanest cloud in the industry. And if you think about what that actually means in numbers, then we actually signed up for more than 60 wind and solar agreements around the world that is new to the grid since 2010. And since 2020, we actually issued $5.75 billion in sustainability bonds that people can apply to. And then in 2030, we want to enable additional 5 gigawatt of renewable investments to the grid. Every Google services, as you know, consumes a small amount of energy, or some amount of energy. So with trillions of searches every year, with YouTube that some of you are probably using, you see billions of hours of videos and upload billions of views. With Google Maps that have monthly more than 1 billion active users, and with 4 trillion photos stored in our Google Photos, and every week adding 28 billion new photos to that database, it all adds up, really. So, of course, we need to take that seriously because we are definitely consuming energy. So, data centers never sleep. We want to make sure that with equipment that is out there performing like computing tasks every day, we want to make sure that that's done in a reliable way. We want to make sure that that's safe and also without interruption. The challenge at hand is that with solar and wind and even utility grids that is not all time available, you need to figure out how you actually become, on one hand, reliable, and on the other hand, renewable, and specifically net zero. So how do we solve that complex problem? Well, first of all, we want to make sure that we learn the utmost, specifically here from Europe, about energy efficiency. So example, from 2010 to 2018, we experienced in the cloud computing more than 2,600% increase. But at the same time, we only increased the energy consumption with 10%. And that's because we relentlessly focused on energy efficiency. So if we look at the PUE, we are considered as being the world leading when it comes to the PUE for our data centers. You can see the graphs up here that we actually are tracking around 1.1. And we're very proud of this, and we'll continue that journey to make it even more efficient. Also, we heard a little bit earlier today that our friends in the industries, in other hyperscalers, have similar agendas about being net zero in 2030. The good news is that we actually achieved 100% renewable energy as a major milestone in 2017 already. And we also declared quite soon thereafter that we wanted to be net zero in 2030. So we want to do that all places at all time. And we're talking about an hour-by-hour basis. And I think that's where the challenge gets so much more difficult. We also want to acknowledge that we are using water to cool down our data centers. We want to replenish that water with 120% replenishment, but we think that water plays an important role in our fight against CO2, because the fact is that water-cooled data centers are 10% more efficient and thereby 10% less CO2 polluting than other data centers. And we want to acknowledge that we need more technology development so we can actually offset this going forward, right? So in 2021, water cooling helped us reduce roughly 300,000 tons of CO2, so it matters. So also, I want to kind of like also address, of course, energy efficiencies and how we actually are thinking about our offset, but also think about the 3 scope of emission, which is extremely important for all of us. As a recap for those who are not familiar with this, which I think most of you are, then scope 1 is the direct emission that you can control. Scope 2 is basically the indirect emissions coming particularly from utilities, and then all other emissions are basically around the supply chain. As we saw today, some data that we are definitely like also focusing heavily on scope 3, because we also see that the similar data as Meta showed today, that there is actually a lot of carbon tied up in supply chains. So some examples of the different scopes and how we work with them. So first of all, geothermal. We actually signed a large contract in US, in Nevada, where we basically are looking into the next generation of geothermal that is using new technologies. And if we unlock some of that potential, we will, of course, move that to other locations where geothermal is possible. We also are continuing to sign more PPAs, which is basically a good example is in Finland, where we are combining wind and nuclear from the grid, and we actually are achieving 94% net zero hour by hour from the utility. In Denmark, where we have our newest data center constructed, we are seeing like from the Danish grid combined with solar that we have an hour by hour base of 90% net zero. So it really matters when it comes to working together with utilities and also investing heavily in both geothermal, solar, and wind. If we think about meeting this 24/7 carbon-free energy, it requires more. So since 2018, we actually also have used machine learning to predict and optimize the output of, for instance, wind, but you can actually use that for other renewable sources as well. So with our DeepMind system, we actually predict how the wind is blowing the next 36 hours, and we can collaborate with the utility grids and thereby optimize again, the CO2 footprint of that. Also, we have one of the most powerful networks in the world, so we actually have the ability to move IT loads around, and that's where you can see on the picture below. So we actually are thinking about, or not thinking, but we actually are doing our carbon intelligent computing program that moves load to basically where the sun is shining and where the wind is blowing. And we can actually do that because, again, we have reasonably powerful internet connections between our data centers and out to all of you. For Scope 1, we also have some examples to share, and specifically about if a data center is affected by a power outage, we want to switch to backup immediately in seconds, and we call that standby power. So in Belgium is a good example where we actually installed 10,000 solar panels and combined that with battery technology to make sure that we designed for the minimum amount of generators. Because the best thing you can do is to eliminate, of course, our diesel gensets. Batteries also have this benefit that is actually strengthening the grid and the connectivity with the grid, so we can actually participate in grid services. And also the remaining gensets, we are already running some tests about HVO fuel that we're going to replace as soon as it's getting available for purchase in different countries. Scope 3 is an important one, and you may say the best data center is the one you don't build. So utilize whatever you have already invested in is number one, right? But we also think that we actually have some opportunities of thinking about existing infrastructure that's already built. And one of the examples we have is in Hamina, Finland, where we actually took an old paper mill and retrofitted it to a data center. So we actually reduced quite a bit of Scope 3 by doing so. So we repurposed the electrical substation, the seawater cooling tunnel, and we even repurposed the sauna that was out there. Also, data centers, of course, when we have to build more because of need of capacity, we are going to think about designing for first principle. And think about it, if you take like a data center, you put it on a scale and you see how much it's weighing, right? And you can actually start to think about how much of this mass is actually needed and how much can you take out. And that's actually some exercise that we are seriously running to make sure that we are eliminating as much as material as possible, because then we have to run less material through the supply chain. The one material that we are then using, of course, we're trying to find out whether we can use recycled or even substitute with, for instance, engineered wood for structures and so on. So empowering consumers and ecosystems. So all data center stakeholders have to work together for this challenge. On one hand, you want net zero, and you want to rely on variable energy sources. And on the other hand, you want to have reliability for everybody 24/7. So how do those two meet? Well, Google cannot solve this challenge alone, so we need your help. We believe that data centers have to be affordable, carbon-free, reliable, and help users around the world. But we also believe that we should participate in all of this OCP work with transparency, make sure that we are working with stakeholders to make a global impact. And we also want to make sure that we are continuing to share our learning with the open source approach for innovation, and also enabling partnerships so we can solve those complex problems together. So we are poised to success with this OCP framework, so I definitely want to continue to contribute and make sure that we are working on this in partnerships. So we partner through a time of tremendous change and growth that we all are witnessing. We, as a company, is actually serving on the OCP board of directors, and we co-lead several of the OCP projects. So we are definitely engaged. Last year alone, we made like 18 of the 74 total contribution, which is more than 20%. So we are contributing to the party, if you will. For security, I'm also excited that the Calyptra have reached the 0.5 milestone, and also the RTL code base have reached the 0.8 version of the Chip Alliance. And that's really important milestones for us, and we believe that moving this forward is important for the industry. This tremendous progress is kind of like only after 6 months, and it's in partnership with AMD, Microsoft, and NVIDIA. So we are very pleased of this collaboration. There is a warning, however. The climate change and the global warming is real. We know that it's now we have to act. We can actually act together, and we are planning on actually starting up a huge investment in Europe about our innovation center, and everybody who wants to join can really join this effort, where we want to work with private and public institutions based on local needs in a European collaboration. And we look actually forward to work with you and innovate with you. And the barcode here is real, so you can scan it and you can actually get some information about how you can be a part of this. We again believe that those challenges need to be solved in a team, and we want to create the framework for that. We also want to acknowledge that we have been working with iMason, the Climate Accord, and we actually just published a paper that was authorized by Microsoft, Meta, and AWS, and ourselves in Google, that describe how we want to deliver more green concrete and talk about more embedded carbon in concrete in generally, because it's quite significant amount of the CO2 footprint. You can read a lot more about it in the paper that was just released. So again, sign this paper, make sure that we are facilitating more green concrete in construction, so we can at least reduce the amount of CO2 that is possible. Finally, to continue to support sustainability, please hang around. There is a panel discussion just right now after me with one of my Google colleagues that is going to talk about sustainability more. And also join tomorrow where Googlers in our company are delivering more on sustainability and security in generally. So I want to thank you for your attention. I hope that you kind of like enjoy the presentation. We have, of course, a ton of more data behind all this that I will be more happy to share in some networking discussion later on. So thank you so much.
Please welcome Google's Sustainability Lead Data Center Innovation, Priya Chiba.
Ahoy, Prague. Welcome, and thank you all for being here today. Wasn't it wonderful to see all our keynote speakers focus in on sustainability? Some of the key themes that I heard today was sustainability and collaboration. So JP mentioned that in his keynote presentation a few minutes ago, and DJ highlighted that a few minutes ago as well. So today we have a really exciting panel where we will be discussing how we as an industry can collaborate cross-organizationally on sustainability. So with me today, I have from Cirrus One and representing the CNDCP, Matt Pullen. Give him a round of applause. And then from KO Data, I have Jared Thibault. And then from the RISE Institute, I have John Summers. Hey, it's really nice to have you all here. Welcome, and thank you for joining me today. So why don't we start off by letting you introduce yourself. So Matt, why don't you tell the audience a little bit about yourself?
Sure. Matthew Pullen. I don't normally steal people's chairs.
That's okay.
My day job's to run the European business of CyrusOne, where we currently have approximately a dozen hyperscale colo data centers across the key European markets. But most importantly, I'm here representing the board of the Climate Neutral Data Center Pact.
Thanks, Matt. Jared, how about you?
Hi, thanks very much, Priya. Gerard Thibault, Chief Technical Officer of KO Data. I've been in the data center specific arena for the last 25 years, starting off back in the Global Crossing days of establishing the pan-European network. And really my role at KO Data now is to drive innovation and focus on sustainability. And I'm part of the OCP Committee on Sustainability for the Data Center Facility Project.
And John?
Yes, so it's John Summers. I am actually scientific lead at Research Institutes of Sweden, and before going there I was 25 years as an academic in the UK. And I guess I was born on the flashing cursor line. I've been programming a lot all my life in the research. And then obviously the computer became a problem, with the thermal management. That's where I got into actually data centers, trying to manage the energy and the thermal aspects.
That's awesome. Well, aren't we lucky to have all of these panelists here with us today? So, DJ talked about something. He introduced the topic of global surface temperatures. And the IPCC recently published a really alarming statistic. So between 2011 and 2020, it appears that our global surface temperatures are 1.1 degrees Celsius higher than it was between 1850 and 1900. So that is really eye-opening and sobering to some extent, because what it highlights is we have limited time to combat or mitigate climate change. And John, this question's for you. So, what is RISE doing in the cutting-edge research area to help mitigate climate change? And, how can we as data center operators support you in some of this research that you're working on at RISE?
Anna, thanks for the question. I think it was great that DJ mentioned it's a Swedish affair, Svante Arrhenius. Being in Sweden myself, I have followed his work. Our first and foremost thing that we've been looking at when we started some of our research initiatives five or 6 years ago was looking at energy efficiency. So this is where obviously we consume electricity into the electronics, and if we can consume less and do just the same job, then we're walking in the right direction. But I think it's become a little bit more than that, from the operational side. We're trying to understand operational temperatures, et cetera. What temperature should we be operating at? And I think, there is one or two talks this week about, how hot should we be running our data centers, from an energy efficiency perspective. But I think, now our research in terms of collaboration is really trying to say, well, you bring all this energy into a data center, which has a good exergy, and then the exergy is destroyed, and then we do nothing with that. So I'm talking about the possibility of heat reuse. So we've looked at a lot of, with collaboration, this is really where you need collaboration. Data centers can't do this by themselves. So the synergies with other industries that would use, am I cutting out a bit?
You are cutting out, yeah.
So that's the important thing, is that. But I think now we're starting to look at the initiatives around the scopes of emission. And I think one of the things, data centers are not really the problem. It's everything else that's the problem. I mean, transport and heat are big consumers of energy, primary energy. And can the data center be part of that? And yes, they can, mentioning heat.
Yeah.
But also, can we avoid transport? Yeah, there's been proofs of that in the pandemic. Can we reduce so this could be avoided emissions. Some people are calling this scope 4 emissions. So if we can avoid emissions by using digitalization, and that's part of the research. But this is a collaborative effort.
It's really great to see RISE focusing in on so many of the things that I wanted to talk about today. So I want to dive in firstly to some of the regulations that's been put out by the European Union through the European Green Deal. And I believe there's some changes coming through the pike in 2023. So Matt, can you educate us on what's coming down the line and how can we prepare for those changes that's coming through?
Sure, I'll do my very best in just a few minutes. As you say, it all starts with the European Green Deal, the vision that Europe as a bloc will be climate neutral by 2050. And within that vision, Brussels would like data centres to be carbon neutral by 2030. So Brussels is effectively relying on existing legislation, upgrading legislation, and introducing new legislation to realise the vision. Good example of existing legislation, EU taxonomy, which is there to effectively categorise sustainable investments by the biggest companies and financial institutions in Europe. And as part of that, data centres are effectively directed to align to the EU Code of Conduct as it relates to energy efficiency, and also embrace a number of European standards that represent best practice on energy efficiency. Good example of an upgrade to legislation, and really picking on what could happen this year, the European Council and Parliament have determined that as it relates to the Energy Efficiency Directive that's been around for at least 15 years, they want to make some additions. And they're talking about a stretch target of 11.7% on the energy reduction target, which overall is 36% by 2030, before the stretch target relative to energy usage in 2007. When it comes to data centres, they would like to see data centres with a capacity of 500 kilowatts or more reporting on their energy efficiency and sustainability metrics by May of next year. They would like to make it mandatory for data centres of a megawatt or more to reuse their waste heat, with the caveat where it's possible and where it's economic. And I think also by the end of the year, we're probably going to see proposals come forward for an energy rating system for data centres. So just touching on the pact, if you want me to just
go ahead.
Do that. So the pact was formed just over 2 years ago by the European Data Centre Association and CISPE. We have over 120 signatories, and that represents more than 95% of the industry, cloud companies, colo providers, and national trade associations. The original vision was a self-regulatory initiative, and we've been setting targets to help get the industry to climate neutral by 2030. The reality is there's going to be a lot more legislation. And so we're using the targets to really discuss with the Commission the art of the possible and prepare the industry for the legislation.
Yeah, that's great. So Gerard, all of this must be really confusing for you as a data center operator, right? You're part of OCP, you're a member of the pact. How can the organizations represented here today support you in your decarbonization and sustainability goals? And maybe you want to share a little bit about what KO Data is focusing on from a sustainability perspective.
Sure. Firstly, collaboration is absolutely key to making this work. We need to share ideas, and the OCP in particular is a great way of doing that. I've learned a lot. Certainly, we're working with Mark Dancy on the OCP Ready checklist. Tying into the Climate Neutral Data Pact, again, is very important. It's given us those 5 pillars to look at, and particularly focusing in terms of KO Data sort of strategy, where really sustainability and efficiency is at the heart of what we do, and me as an engineer. We've sort of focused on energy, so we try to make our data centres as efficient as possible. We're operating at around about 1.2 on a per suite basis. But even when you look at the overall, if you measure it on the green grid sort of scale as the complete facility, even with the drag of the administration, we're under the 1.3 target. And that's with a data center load of about 16% of overall. And that's quite a key in looking at the performance across the whole band. We've done things like buy into REGO 100% renewable energy contracts, which over a 12-month period are great, but obviously one of the things we're striving for as part of our technology plan is to make that 24-hour, hour-by-hour carbon-free. So we're looking at our own private wire, local solar, battery energy storage, although we have contracted and paid a premium to bring in a specific wind farm into our facility. Incidentally, I mean, JP talking earlier, it's almost like a replay of some of the things that obviously you're doing. In June 21, we switched to hydro-treated vegetable oil to try and drive down the greenhouse emissions from generators and fossil fuels, so we don't use fossil fuels on the site anymore. But in reality, it's a fairly small chunk because you don't run your generators very much.
That's right.
Hydrogen fuel cells play into that, but again, there's capital and operating cost penalties for those. So they're part of the scene, but again, collaboration, and Madhu on the Ampere presentation, focusing on driving down the one of the PUE is very important, I think.
That's right, yeah. Especially with some of these newer technologies out there, like it's really interesting to share ideas and, you know, lessons learned so that I think we can accelerate the transition, right?
We need to.
Yeah. So, you know, a recurring theme that I've heard between the three of you is energy efficiency. And I wanted to share or reshare a tidbit that JP shared in his presentation. So between 2010 and 2018, workloads hosted by the cloud data center segment increased by 2,600%. But at the same time period, the global energy use of all data centers rose by only 10%. So I think from an energy efficiency perspective, as an industry, we've been doing a great job, right? But Matt, I know the pact is very focused on continuing that trend of improving because it still gains that we can make in the energy efficiency realm, right? So can you talk about some of the targets that the pact has set? I know they're very stringent targets, and you know it's self-regulated too. So yeah, can you tell us a little bit about that?
Yeah, sure. As I said earlier, I do think there's a lot more legislation coming, but the setting of a self-regulatory vision is great because it just enables the dialogue with the Commission. But if the pact is focused on 5 pillars, as Jared mentioned. So we've got clean energy, energy efficiency, water conservation, circular economy, and circular heating systems. Circular energy systems. We've been running working groups across monitoring and reporting, energy efficiency, water, and circular economy. I think the big achievement of the monitoring and reporting group was to actually develop and publish this year a audit framework so that small, medium and large companies can demonstrate alignment with the Code of Conduct, was effectively one of the main directives. Interestingly, that initiative was spurred on by SAP, whose auditors couldn't find any way of auditing them against the Code of Conduct. So the pact has helped to achieve that, which is great. On energy efficiency, Jared mentioned the targets that have been set initially, 1.3 in a cold climate and 1.4 in a warmer climate for the PUE. But the energy efficiency working group is really working on trying to solve for the 1 now. The water group developed and the pact agreed the WE matrix target. So for example, if you have a data center in a cold climate using potable water, but where there's water stress, the target is 0.4 litres per kilowatt hour, for example. The circular economy group has just got started, and I think the call to arms piece is always that we can't really run concurrent working groups because the signatories provide resource on a pro bono basis. So you just have to prioritise. So I'm really proud of what the pact's done, but without doubt we can do a lot more.
Yeah. And John, on the research side, you touched on energy efficiency at RISE, and can you tell us a little bit about the projects you have going on, and how those projects can benefit us as an industry?
Yeah, I mean, one of the projects that I can probably refer to is we did win an award for it. It was the holistic cooling control. So this was trying to get the things synchronized so that everything runs a lot slower. Like, you know, with your compressors, you can variable speed compressors, variable speed drives, you can slow things down. And that, from your cooling perspective, that is a good way of getting some energy efficiency. But the other thing is obviously, there's two parts to this energy efficiency in my book. There's the physical limits of computation, which is on the one side, and then there's the other part of it is how effectively or how well we get the heat from where it's generated to where we can either consume it or reject it. And if you think about it, these microprocessors are running at 50, 60, 70 degrees, you know, and that's very useful heat if we can get it at that temperature. And it goes back to this argument about exergy. But I think we get ourselves really tangled up with efficiency, the metric efficiency, and I think I put out a LinkedIn post just recently which got me into a little bit of trouble, because the energy efficiency of compute is very difficult to define. Because, you know, in engineering terms, efficiency and energy efficiency is what you want divided by what you have to pay for. What you want are the digital services, what you have to pay for is the kilowatt hour. Now, how do you measure the digital services in terms of energy, in terms of kilowatt hours? It's very difficult to do. So we still have, from a research point of view, quite a bit to do there. And I think maybe, you know, we should be looking at it in a different way. And maybe there is no such thing as one metric. And I think we may come back to this a bit later, but, you know, the PUE is not an energy efficiency metric. It's a metric that has been very useful for the industry to progress and become more effective at the way it operates around the one.
Yeah.
But it doesn't really say anything about the efficiency of the compute.
Yeah, I think if you look that way.
Yeah, is it? Yeah, I'll look that way. Should have known
So regarding PUE, I know you have some thoughts on how that metric can be improved. Do you want to talk about that a little bit?
Well, I think, yeah, I mean, when we talked about improving it, it's a difficult one to improve, because the great thing about the PUE is it is a very simple metric. And simple metrics are very useful in this industry because it helps. And of course, we've been mandating against PUE. But if we are going to use PUE, I think we really need to use it as it's defined in the ISO or in the EM 5600, whatever standard you can get access to. I mean, it's well defined there. But it's still, I think it's not just one metric again. I think it needs to be, and there are 6 good metrics that are mentioned in the Energy Efficiency Directive that are useful. And of course, we mentioned water as being one of them, but also the energy reuse factor, which is something that would be helpful.
Yeah, that is one of the new metrics out there. And talking about energy reuse and heat reuse, so Jared, you know, heat reuse and capturing data center heat is one of the hot topics, especially here in Europe, and there's going to be requirements for heat reuse coming out, as Matt mentioned. What are some of the challenges that you see out there in industry in tapping into some of these heat reuse networks and to making your heat available for use?
There's a lot of practical problems. Some of it is around no one solution is going to fit the world. So we've got to look at different solutions for different regions and even localities within those regions. UK specifically doesn't have a good history of providing heating networks, but the heating window that's required is very, very small in reality compared to some of the Nordic countries where they're sort of more ubiquitous. In terms of actually providing the heat back into the system, I mean, I think it's a great idea, without doubt. Just to waste it into the atmosphere is sort of nonsense, really. But we need to look at the operating efficiencies and balance those and look on a case-by-case basis. We tend to use as a basis of design in Northern Europe, because it works well, air-to-air heat exchangers. For most of the time, they run dry, and it's just fans circulating on either side of a plate heat exchanger, which means that the PUEs are sub 1.2. And that's great because we then use less energy. But if you try and recover that energy, firstly, it's only 32 degrees centigrade, so it's very low-grade heat. You've then got to, that increases the pressure drop through the system, so increases your fan power. You then need heat pumps to boost the value of that heating up. So actually, you've got to then make a judgment. Would it be better to heat direct rather than do that?
Boosting it, yes.
Part of the problem is that we can't, as a data center operator, guarantee the amount of energy that we've got to give to the network. So because our customers drive the one, we can't determine whether that's going to be fully utilized or not. So we can't make commitments to resell that power unless we know it's there for definite. So that's a conundrum that's very difficult to solve. And even the regulatory thing about reselling power is very difficult to sort of find all the ins and outs of, to be honest.
Yeah, yeah. And I think, John, you had an interesting tidbit about a Finnish company and a...
Well, yeah, it was actually in Sweden, I think,
okay.
Because there's quite a lot of initiatives around heat reuse in Sweden and in Finland as well. But the issue really is that you have a cola provider who is providing, who has a heat pump. Well, in one situation, the heat pump is owned by the heating operator. And in another situation, the heat pump is owned by the data center. So when you do your PUE calculations as per the ISO, you suddenly find that your PUE is greater than 1.2. So there you are, a colo who's trying to sell space to somebody who wants the space, whose mandatory requirement is to be sub 1.2. And sorry, but I'm reusing the heat. But that's where the energy reuse factor needs to come in. And there was a metric that the Green Grid had that never became an ISO metric, which was called the energy reuse effectiveness, the ERE, and it was a combination of PUE and ERF, and I think there was a reason why it was never put forward as a metric. But the two metrics together really need to be seen together in order to have these kind of conversations, and I think it's an education piece at the end of the day, isn't it?
Yeah, yeah, and within the data center facility sustainability track, we are looking at metrics, and maybe that's something we can look at is what sort of metrics should we incorporate for heat reuse, and especially when it comes to justifying some of these projects, as you mentioned.
Yeah, because often you've got double CapEx installation. I know we're short of time, but the operator has to put in heat rejection in case you can't reject to the local district
That's
network.
Right.
And vice versa, if they can't get the heat from us, do they invest in other heat generation? So, yeah.
Well, you also have to look at the seasonality too, right?
Yep.
Because the heat may not be required at all times of the year.
Sure.
Well, that's a good point, because the example was that they could only reject the heat between September and May. They still have to deal with the heat in the summer months. And I think, putting more plant in, I think one of the things that we haven't talked about probably today at all is that we've been focusing on energy and carbon, but there is an issue around resources, resource sufficiency and the use of materials.
That's right.
Critical raw materials.
Yeah, and I think we'll have to hold that for another conversation. We're running out of time, so thank you all. So how can you support us and continue this conversation? We have, as DJ mentioned, started a sustainability track with an OCP, and then we also have a data center facility sustainability sub-working group where we recently launched 3 different work streams. One of them is focused on energy, power, and heat reuse. The other one will be focused on construction emissions reduction, which we didn't really touch on today. And the third one is metrics focused, as DJ mentioned. And so we really would appreciate you joining, contacting us, joining, signing up, and participating, because, as we all mentioned, we need to work as an industry. If we are going to combat climate change, we need to do it together, and we need to share resources as we do it. So thank you all. Thanks.
Once again, please welcome back George Chaparian.
Okay. I am standing between you and lunch, so I'm going to make this very short. So I just want to first thank our keynote speakers. I mean, really appreciate their time and energy and helping us with the very informative, topics and subjects, as you have seen. In the afternoon, I encourage you to go to the Future Technology Symposium and also the Sonic Workshop. I think it's going to be very enlightening, and you should really attend those. And also tonight, we're going to have a reception. I'm looking forward to mingling with you and having a couple of beers and get to know you. If there's anything we can do to help you, myself or my team, please find us. We're wearing badges, I believe. And day 2, it's going to be full of engineering workshops again. And don't forget to go to and see the expo hall with a lot of innovative ideas from our sponsors. So finally, I would like to thank all our sponsors that help us and make this possible. And also, I will call the Fentech folks who are really the invisible hands putting this together. Thank you again. Enjoy the summit, and let us know how we can help. I really appreciate it. Thank you very much.